This year's first shuttle flight to the International Space Station starts building the framework for power and cooling capacity that will enable expanded scientific research in the coming years. The astronauts of Shuttle Atlantis and the Expedition 4 crew members will install the keystone of ISS's 356-foot-long integrated truss assembly, a segment named S0.
If you ever looked at a picture of the International Space Station, one of the predominant features that you see are these huge solar arrays, bigger than the size of a football field. And those arrays have to be supported by something, and what they're supported by is this big truss. And S0 is the part of that truss that actually attaches to the International Space Station, so it's up on top of the laboratory.
The whole goal of putting S0 onto the space station is to start this next phase. It's sometimes called phase 3 of the space station build, where we will increase its capacity to do research. Right now it has all its basic capacity to do spacewalks and maintain human life, etc., but now we need to increase its scientific capability.
Filling the shuttle payload bay, S0 is a 44-foot-long, 15-foot-wide aluminum girder. It houses electrical transformers and switching units, lines to transmit power, cooling fluids, data, and video into the space station, an array of global positioning system antennas and rate gyroscopes to complete the guidance and navigation system in the American segment of the station. And along its front face, S0 carries a 1,900-pound aluminum flat car called the Mobile Transporter, which, along with the Canadian-built Mobile Base System, due later this year, will enable the space station's Canadarm2 to ride the rails of the station truss. Installation of S0 and the Mobile Transporter take place over 4 spacewalks by 2 teams of shuttle astronauts, led by mission specialist Jerry Ross, the man with more spacewalk experience than any other American astronaut, the man who made history on launch day when he became the first person of any nation to launch from Earth as many as 7 times, a man who was fascinated with space as a boy years before the first Sputnik ever circled the Earth.
And I felt very fortunate that I felt like I had some divine guidance at a very young age to help me focus where I wanted to go with my life. And through a lot of hard work and hard study and good breaks and I think some intervention from above, I've been able to get here.
The spacewalkers will work in conjunction with the robot arms on the shuttle and the station. Pilot Steve Frick flies the shuttle arm to provide camera views, as flight engineers Carl Waltz and Dan Bursch and mission specialist Helen Ochoa alternate at the controls of the station's big arm.
Because the station arm is so big and the viewing is not as direct as we have for the shuttle arm, we typically have 2 people, one running cameras and then one actually flying.
And while they can do some types of training on orbit, it really helps to be down here on the ground, working directly day-to-day with the spacewalkers or with any last-minute changes to the install. So I'll have sort of the up-to-date information about all the tasks, whereas Dan and Carl will bring to the table the actual flight experience of using the arm.
My main responsibility will be working the robot arm and working with Ellen on installation of the S0 and EVA-1, which will be on the same day, and then EVA-3. Carl's main responsibility will be working the arm, working EVA-2 and EVA-4.
First priority, connect S0 to the station. Ochoa will lift S0 out of the shuttle payload bay and move it into position above the lab. Bursch takes the controls to mate S0 onto the lab cradle assembly. Then Smith and mission specialist Rex Walheim exit the Quest airlock, which for the first time will support all spacewalks conducted during a shuttle assembly flight. Anchored in a foot restraint on the end of Canadarm2, the first time it's been used to maneuver spacewalking astronauts outside the station, Walheim goes to work on a pair of module-to-truss structure struts located on S0.
The first goal is to structurally attach the S0 to the space station. So that's the big thing. And the way we're going to do that on the first spacewalk is to attach the forward struts. There's 4 sets of struts that hold S0 down to the laboratory module. And we will release and swing down these forward struts and then bolt them onto the station.
After solidifying the mechanical connection, The astronauts will concentrate on 2 trays of cables that will form the electrical connection.
So Rex will go up to the top of the truss with the arm, take these 2 very large umbilicals down to the lab, place them on top of the laboratory so they will attach physically to the laboratory. Then at both ends he will attach electrically the truss element to the lab,
enabling station power to flow to the heaters that will prevent the systems on S0 from freezing. On the front side of the truss, they'll connect a reel of power and data cable to the mobile transporter. And on the rear face, they'll hook up a tray of cables to their mates on the station's Z1 truss. On the second spacewalk, mission specialist Lee Morin will ride Canadarm2, while he and Jerry Ross bolt S0's rear struts to the lab.
And I'll remove some bolts and take a large strut, which will be one leg of a tripod. And I will move that loose leg of the tripod, and the tripod will form and come down and be pointing down at Jerry, who will be down waiting at the lab to get that. And he'll bolt his end in, and I'll bolt my end in.
After they install the 4th module truss structure strut, Ross and Morin connect a second power and data cable reel to the mobile transporter and remove hardware that held S0 secure in the payload bay during launch. Canadarm2 gets unplugged for the 3rd spacewalk, so Smith and Walheim can reconfigure the space station arm to receive power through S0, so it can eventually walk onto the mobile base system. With Frick at the controls of the shuttle arm, Smith will ride to the top of the laboratory module to redo power connections there.
And then we go all the way out around to the bottom of the lab, which should be kind of interesting to see on video, because in order to get him there, we have to swing Steve way out away from both the lab and the shuttle. So he's going to have some views of both the station and the Earth that no one's ever seen before, being that far away. And once we get him to the bottom of the lab, he's going to change a lot more connections in order to repower the station arm.
They'll also install a ladder to ease translation from Quest to S0 and remove launch restraints from the MT. That will permit the mobile transporter's first movement on the railroad track running across the face of the S0 truss.
There's 2 sites where it can park, if you will, on this railroad track. And so we're going to move it to both of those sites and make sure that when it gets to each of the sites, it can hook up with some connectors that are at each of those sites.
The 4th spacewalk is an opportunity for Ross and Morin to wrap up a variety of jobs. Things like
installing a couple of lights on the outside of the station. We will be installing those handrails that we took out and placed a bag out there on the 2nd EVA. We'll be taking those handrails out and installing those on the outside of the truss. There's 2 shock absorbers, energy absorbers, that we're putting on both ends of the mobile transporter. It's a way of protecting it and other hardware should something get stuck or jammed on the track as these various different units are going up and down the track.
Even though this flight is primarily devoted to station assembly, it will contribute to the scientific work already underway by delivering research supplies and equipment, along with water and personal supplies for the crew members.
The items that we're transferring probably fall into 2 categories, and one is the science experiments. So we are changing out a few of the experiments, bringing up some new ones for them to operate, and taking home some of the ones that they've actually been working on for quite a while. And then the other category would be just operational or personal items like laptop computers, transferring water, things like that, extra spacewalking equipment, things that they need to live and work every day on board the space station.
Onufrienko, Waltz, and Bursch expect another 8 weeks on orbit after Atlantis undocks for the 2-day trip home, and a planned landing at the Kennedy Space Center in Florida to wrap up the 2nd shuttle flight of the year.
Good morning and welcome to the STS-110 pre-flight briefings. First up on today's agenda is the International Space Station Program interview. With us this morning are Tommy Holloway, International Space Station Program Manager, and Mike Suffredini, Manager of ISS Operations Integration. Tommy?
Well, good morning. It's good to be back with you again. It's been a while since we had an assembly flight to the International Space Station. I believe it's been 9 months, Mike, since we last launched the airlock. But in the meantime, things have been going very well on board the International Station. We've launched logistics flights and utilizations flights and are increasing continuing to increase our payload operations and our utilization program in that process. We're in the final preparations for launch, first in a series of trusses. We'll launch 3 this year, and they provide the framework for the power and the cooling, external cooling for the International Space Station. A very important series in the critical path of eventually completing the building of the International Space Station. We'll launch 50 tons of hardware to the station this year. We're now at 300,000 pounds, about a third of the way there. Sometimes we think we're about done, but we really have a lot of work left to do in the next 2 years to get to a point where we'll then be ready to deploy to international partners. The last 18 months, 2 years have been really an incredible period from the standpoint of what has happened as all of this has come together. We've flown 21 flights to the station since July the 12th of last year. And in that count, by the way, I'm counting the progress that's on the way. I'll assume that it's going to make it, that we're going to launch later today. Those flights are going very well, extremely well, exceeded my wildest expectations, as a matter of fact. We've had a few problems along the way, but the engineering team and the flight operations team have overcome those in their normal, exceptional way, and the work has all gotten done extremely well. So if I sound like I'm well pleased, you're reading it correctly. Expedition 4 crew has been doing a really phenomenal job in continuing the work on the station. They not only take care of the station in the day-to-day operations, but they're continuing to the payload operations and building upon what their predecessors have done. We are working a problem with the remote manipulator in one of the 2 redundant strings, avionic strings that operate the remote manipulator. And we have a satisfactory solution for that will provide a backup capability to operate that redundant string should the other fully functional string fail during the operations. And Michael, I'll talk to you a little bit more about that later. The S0 that we'll deploy on this flight, on 8A flight, is a very complicated element in the station. Probably the second most complicated, the first being the U.S. laboratory that we'll deploy, and has some 475,000 parts, for example. It'll be the first time that we will have used the arm. Second time we used it in the airlock. It's the second time we've used the arm to do deploy operations out of Shuttle payload bay, and so S0 is a very important flight coming, and at this point we're ready, proceeding toward being ready to launch it on time on April 4th. Mike?
Let's see, I thought I'd take a moment and just describe to you what it is that we're about to fly and show you a depiction of the hardware. So if we can go to the still, you'll see in this picture here across the top of the lab, that's all 3 of the elements we plan to fly here in O2. In the middle of that section is the S0 truss. You can kind of tell how it's different than the elements on either side if you sort of divide that by 3. The middle section is the S0 element. It launches here on April 4th, as Tommy mentioned. In addition, then the S1 truss comes up next, which is on the left-hand side of your screen there. It's the starboard truss. It carries up the central cooling system for the International Space Station. In that picture, you can see the large radiator panel. Only one of the 3 panels are deployed in that picture there. And then on the right-hand side of your screen is the P1 truss. Let's see, the S1 will come up in late summer time frame. The P1 is probably in the late fall time frame. P1 will come up, and then we will install it, and with the completion of those three components, then we have 133 feet of the truss installed on the lab, and we're ready for the power modules, which will come up next in 03. And just to give you a feel for the size, if we could go to the video, we have a video of the crew working in the neutral buoyancy lab. This again is all three segments. You can see P1 in the upper right-hand corner of your screen, and S0 in the middle there over the lab, and then P1. Let's see, that's P1 right there. Excuse me. The crew member in his suit, you can see he's about at the interface there. So that's P1. You can see how large the truss is compared to the crew member. As we scan across, then there's S0, and then we'll go across, and that's the S1 truss. S1 and P1 are relatively identical to one another. As I mentioned earlier, they bring up the central cooling systems for the entire U.S. segment of the ISS, and then in 03, of course, we'll begin bringing up the power modules. So it's the beginning of a very exciting time for us from an assembly standpoint as we put these major truss elements together.
Okay, thank you, Tommy. Mike, we'll take questions now, starting at the Johnson Space Center. Please remember to wait for the microphone and state your name and affiliation. Mark?
Thanks, Mark Carreau from Houston Chronicle, and I think it's for Mr. Seferdini. It's about the ARM issues that you're working right now to make this mission feasible. Could you sort of go over whether this is hardware, software related, and what your strategy is to make the ARM work if the second, I guess if you got one string, but if the second string causes a problem?
Yes, we have, sure, I'll go through that. We have tested the ARM as part of normal testing a couple of weeks ago. When we went to operate the primary string, the brakes would not release. Subsequent testing of the redundant string, the ARM was fully functional on that string. And so, Mark, as you mentioned, we do have one string that's fully functional. However, programmatically, we don't like to launch into that condition. We like to have our redundancy. And so in troubleshooting, we have isolated the problem to the wrist roll joint. That's one of 7 joints on the ARM. And we've isolated it as a hardware problem. It is not related to software. The Canadian Space Agency, who developed the ARM, is developing a software patch for us to be able to operate the ARM with 6 of the 7 joints. We have modified our trajectory somewhat such that we can, if we have to go back to the primary string because of a problem with the redundant string, we have developed a plan that will allow us to remove the remove S0 from the payload bay. We have at one point, we have one wrist roll joint maneuver we have to do, and we'll bring the EVA crew out. They have a way to attach a tool to the joint and rotate that joint. And so what we do is we bring it partway out of the bay. As we clear the bay between the ISS and payload bay, then we bring a crew member up on the SRMS. He would rotate that joint about a little over 180 degrees. And then the crew would continue to fly the ARM as they're used to, all the way to the lab cradle assembly on top of the lab. So we're back to having full redundancy of the SSRMS. The patch will be delivered to us next week sometime. We'll uplink it and actually test out the ARM on orbit in this condition on April 1st, and in preparation for the launch on the 4th. And so we believe we've figured out a way through this one, and we'll be good for S0's flight.
And I'm just looking down the line, maybe jumping the gun a bit here, but will you have to make a hardware repair? And I guess where I'm going with the question is, the ARM is integral to assembly of future truss sections, as I understand, and other hardware down the line. Where does this put you in relation to your planning to do that? Are you prohibited from further assembly without a repair, or can the strategy you're using on this mission also work down the line?
Of course, Mark, that's a complicated question, but let me talk to you about what we choose to do, not what we had to do. it would be possible to use the kind of workarounds that Mike mentioned with the current configuration and continue the assembly sequence. Particularly, we believe for S1, we could make it work quite well. However, because we're concerned about understanding the failure and its potential long-range ramifications and being prepared to deal with those, we currently have a preliminary plan to change out the wrist roll joint on UF2, the flight that's scheduled for May 6th. That would involve adding a spacewalk to that flight and installing a new wrist roll joint that would be launched in the cargo bay. If we make that decision, and the work is pretty well completed at this point, it would result in the flight slipping into probably May the 31st. So we'll converge on that in the next day or two and announce that at the appropriate time.
Okay, Marcia?
Marcia Dunn, Associated Press. A couple of questions for Tommy. I think everyone is so impressed with the technical achievements of the past year and a half, but this budget problem and the accounting problem keeps cropping up. And I'm wondering if you could take a minute to explain in your own thought, in words, how it came that the new administrator can't even perform an audit of the space station books and explain to Congress how much this is going to cost America.
First of all, Marcia, I think we're mixing up apples and oranges. The audit stuff that you've been hearing about is a global audit about where all the money in NASA has gone over a period of time, and I believe is unrelated to the station cost situation. Now, relative to the station cost, I believe the primary concern is whether the station program has a credible, high-fidelity cost estimate that the administration and the administrator can stand behind in terms of what the future cost of the space station is going to be. Now, we have and have had since last May or so, our estimate of what the cost for the station would be in this budget horizon, particularly. And the budget horizon is what I mean by that is that's how far in the future in the federal budgeting process that we submit estimates. That's been in place since May. Now, what we're currently doing is a three-pronged effort to improve the fidelity and the confidence that we have in those estimates. Space station program is going through a process of what we call re-engineering and doing a great deal of work to reduce the cost, to save money, and going through the process to update our estimate of what it would cost to do the station program, including what we call life cycle costs, the total cost to the end of the program. In addition to that, NASA has an independent team that is doing an equivalent thing in parallel with that. In addition to that, we have an outside team led by DoD cost estimation experts that will come in and do in parallel a cost estimate. Toward the end of the summer, we will reconcile. There no doubt will be differences in those three pieces of work, and we will reconcile all of those numbers and discuss them and present the data to NASA, internally to NASA, and then to the OMB and the Congress. And if all works the way I expect it will, we will then have a credible cost estimate for completing the International Space Station, and the administrator can go forward with his plans to with some confidence that we now have a credible estimate for the cost of the station. I believe in general that, and back to your earlier comment of why we can't account for it, I can assure you that we know where all our money is and we know where all our money is going. We do not have any accounting problems internal to the International Space Station. I also do not believe that we're wasting any of the taxpayers' money in doing this phenomenal technical job that you just talked about. I think we are watching our money very closely. We're working very hard to make sure we don't spend any more money than we have to do the job not only technically correct but safely. And so at this point, I'm very proud of the team that's doing the financial management as well as the technical.
What about this has been so hard to estimate costs? I mean, and you say you had an estimate last May. I'm wondering what that is, if you can share that. And what is it, because it's new? Because it took longer to get everything up there than you envisioned? I mean, what led to this point? A couple things that you'd like to cite.
Well, you need to put that in the context of why is it costing more than what someone said it might cost in 1993. And there's probably many reasons for that, but two or three at the very top level. First of all, I think there were many things that were not properly identified that really needs to be done in the initial estimates of how much the program would cost. The second thing, and as has been required over the years, we have added those things because we thought they were necessary and prudent things to do. The second thing that's happened to us is our schedule has gone to the right. And it depends on which direction you look from the precise number, but in round numbers about two years in terms of where we are today. In terms of assembly complete, it's more than that because the flight rate between now and assembly complete has been spread out. And the natural results of things moving to the right causes the total cost to go up. So that was the second thing. The third thing that the agency and the review committees were concerned about is our ability to more rapidly understand the dynamics in real time of what's going on in the budget and in the operations. We do need to do some improvement in our ability to be able to understand in real time what is happening to our budget situation and how much work we're getting done versus how much money we're spending, and account for that and keep up with it in a more expeditious way. So we're putting things in place to enable us to do that. So I think in summary, those are the three top things. And of course, in general, it's much more complicated than that. But I think that at the top level would summarize it.
And do you have an estimate? You mentioned that estimate in May. Do you want to share that, or?
Well, over the budget horizon, we currently in the President's budget, we're budgeted for about $8.3 billion through 06. I believe that ultimately the program would be able to complete the core, to execute the core complete program on $8.3 billion. And the process that we're going through this summer will verify that.
David?
David Santucci with CNN. Are there any other problems on the ISS that could cause the delay of this next mission?
Mike, I'll let you answer that since you work on that. That's your life every day.
But currently on ISS, we're in good shape. I don't know of any problems that we're dealing with today that I think would be a constraint to launch. We have dealt with a few issues along the way, but at this point, the station's ready to go. The crew's ready to accept them, and we're not working any major issues that could be constraints to launch.
Okay. The second question I had is with the limit of 3 people on board. We've talked about the amazing technical advancements we've had. What about the scientific advancements? What's going on right now, and how has that been limited by the crew of 3?
Well, again, there's no simple answer to that question. First of all, if we had another crew person to work on payloads, we could probably do a few additional payloads. But at this point, quite frequently, we're limited by how much payload hardware that we have on orbit and how many experiments we have on orbit. So at this particular point, while we're building the laboratory, if you will, while simultaneously using the laboratory, it's a balance between what we have on orbit, what we're able to launch to orbit for logistics and assembly and payload operations versus how much crew time that we have. And as of this current period, it appears to me that we have a fairly balanced program in what we're able to do. Now, I'm not prepared to tell you precisely what's going on, what the results are, but the people later today could do that for you. The crew's ability to get payload operations done has been, I think, very remarkable.
More questions here? Mark?
Mark Carreau from Houston Chronicle, and I guess this is probably from Mike. I read a news account that raised some questions about the Russians' funding situation again and their ability to provide Progress supply craft into the future. I just wonder if that's something you're working at this point, or whether you have shuttle redundancy if necessary to keep space station supplied if that did become an issue, or maybe this is all false. I don't know.
Well, we're working with our Russian counterparts. They do have funding constraints along the way. We are going through an exercise now to look at the number of progresses they can provide through the end of this year. It's looking like it will be 3 for this year. We have worked those assessments and have worked how we trade the logistics between the Progress flights and the shuttle flights, and we've got our way through that. We believe that we'll have 4 Progresses next year, and we are working the logistics associated with that today. So while it does present challenges to us when we have to change the amount of total up mass that can come up, which is what missing 1 Progress does to us, we have been able to work through that, and we'll continue to work through that. I think the Russians are very committed to this program, and so they'll try hard to provide as many Progresses as they can, and I believe that 3 to 4 Progresses a year will be able to be provided by the Russians, and we'll be able to work with that.
I have a question for Mr. Holloway too, regarding the truss. I just sort of want to make sure I understand the concept of core complete as it relates to the full truss, the 300 feet plus. Is that all included in that as far as you're concerned, including the addition of all power modules and the move of the current module? Is that kind of where the core complete truss power and cooling system is headed, the whole 300 plus feet?
Yes, Mark. Full capability from a power cooling point of view, all 4 solar arrays. So core complete would include all of the power cooling system.
Okay, Masha?
Marcia Dunn, AP for, I don't know, maybe either gentleman. Could you just sort of give a status report on X-38, where that, how you're proceeding with that, if at all, and also sort of give a description of what's being called the safe haven and how you think that might fit into the eventual space station?
Well, Marcia, if we start at the top, currently a X-38 flight is not manifested in the shuttle program based on our budget situation, and neither is the eventual refurbishment of the X-38 to turn it into a CRV. There are some limited funds in the budget that is being spent to allow the orderly continuation of the X-38 at this point, and in a sense, an orderly termination if that turns out to be the direction that the agency chooses to go. So currently, the X-38 is still alive, but for the long-term plan, it's not budgeted, and it is one of the things that we'll have to make a decision on whether to actively continue or not. Second question.
Haven. Could you just
safe
describe
haven.
what the concept is?
First of all, right now, safe haven is predominantly a concept, and it is not very mature. But in concept, the space haven would be a module, perhaps, that one could retreat to if catastrophic events occurred, such as fire or a depress, where you could isolate yourself and survive until someone rescued you. And of course, the options for rescue at this point would be Soyuzes and shuttles. Such a system would need to have a living area, an area that would take care of the atmosphere, CO2, cool it. It would need a way to provide cooling and a way to provide electricity, because the event that caused you to need to retreat might well have taken out the resources that provide those functions in the global space station. I expect that would be a fairly expensive system, by the way. So at this point, there's trade studies very preliminary trade studies being developed about what a safe haven might be and how it would trade against a possible rescue system. And we're probably 2 months away from completing that.
Okay, we'll move now to Kennedy Space Center for questions. We have reporters there.
This is Chen Earthis for Tommy. Follow up on Marcia's previous question about the budget. IR engineer.
Repeat again.
This is Chen Earthis for Tommy. It's a follow-up on Marcia Dunn's question about the budget. IR engineer, I never studied economics, but I'm wondering why you're saying that stretching out the shuttle flight rate so they'll increase the cost of the space station, when the whole purpose behind stretching out the shuttle flight rate was to reduce costs.
Someone go ahead and tell me. I didn't understand the question.
He was asking a question relative to you hear folks talk about when we stretch out the space station launch dates, it was to reduce costs, and he's asking why do you say it costs more money to stretch out the space station assembly flights?
Why does it cost more?
Right.
Well, it depends on what kind of cost you're talking about. If you're talking about how much money we spend each year, it's cheaper, of course, to slow down and not do so much work. If you're talking about how much the total cost of the program may be in the run-out, stretching things out in general tends to cost you more money. It depends on whether you're looking at total cost and productivity of the station during that period of time. It costs about a quite large sum of money to operate the shuttle and operate the space station, and if you don't have it completed and aren't using it for what it is built to be used, you're not getting very good return on your money. So it's a balance between getting the job done, getting the development work done, getting the process finished, getting on with the productivity or the operations phase of the program versus how much it costs each year to get the job done.
And we'll go now to headquarters for questions, and we'll try to get back to Kennedy momentarily.
Question for Tommy Holloway from Tracy Watson with USA Today. The Safety Advisory Panel in their recent report highlighted infrastructure problems at KSC as a possible safety concern, and members of the panel have said these problems need to be addressed to ensure that the ISS crew is safe. How big of a worry is that to you, the kind of decaying infrastructure at the Cape?
Well, I believe their reference to infrastructure at Kennedy is oriented predominantly at the shuttle program in terms of the facilities at the Kennedy Space Center that support the shuttle processing and launch capability down in Florida, and as such that relates to the shuttle's long-term ability to support the launch capability and be able to reliably and consistently launch shuttles sometime in the future. I personally do not believe that's a short-term problem. It's a long-term problem that needs to be managed, but shouldn't be seen, I don't believe, as a short-term problem.
And we'll go back now to Kennedy Space Center for further questions there.
This is Phil on Earth News. How are you guys hearing us now?
We hear you fine, Phil.
Okay. And Tommy, I was a little bit surprised at the current progress swap sequence, that the current progress undocked before the next progress was even launched. I thought normally there's a desire to launch the new progress first just in case there's a problem, delay, or whatever, so you always have a progress docked. And I realize this is mainly a Russian issue, but have they explained to you why the logic for this particular sequence? And remembering what happened with the previous progress undocking back in December, has anybody looked at the progress undocking video to assure themselves that there's no debris in the docking cone this time like there was last time?
The question was why would we undock before we launched the progress? I believe that's been the standard procedures over time. And of course, we don't want two progresses on the station at one time. And the Russians have a history of being very reliable in terms of being able to launch progresses. The reason you like the progress on orbit is predominantly as a stowage vehicle and a source of consumables, propellant primarily at this point. So the Russians manage that in a way, and when we get to the point that uses the consumables. When you get to the point where the consumables are used up, you've packed up the progress and it's full, and it's time to get it out of the way and launch the next one. At this time, we don't have any heartburns with this sequence that the Russians performed that in.
Actually, Tommy, the sequence always in the past has been you launched a new progress first, and then the day after the new progress is launched, then you undock the previous progress. That's what the question is, and also the issue about whether or not anybody's looked at the video of the current progress that just undocked to assure themselves that there's no debris in the docking cone.
Okay.
Let's see. The answer to the last question is we did video as we moved away from the station. Our Russian colleagues are reviewing that video today. Preliminary indications are there was no problems. I have not personally seen the video, but they did that very specifically, as you know, to look for this problem, and haven't seen anything to date. As far as the other issue relative to launching the progress after they've deorbited the previous progress, that is a change in the way we have been doing it for some time. We have done that before, and you'd have to ask our Russian colleagues specifically why, but they indicate to us that they're They have some concerns now with radio frequencies. I think it has to do with facilities and how many systems they have available to them. And so therefore they don't want to have a conflict with sending commands to progresses when they have 2 on orbit. So I believe it's an infrastructure reason is how they've explained it to us, and you could ask them for more specifics. But as Tommy said, the Russians are very reliable when they say they're going to go launch a vehicle. They've done the readiness review for 7P. They're ready to go, and we have high confidence that they'll launch when they say they're going to. And so we're not at all concerned about this new process.
This is Steve Stanislaw from Florida today. I have a quick one first for Tommy, and that is, what are the odds of flying the new wrist joint on the next mission?
On UF2? I think it's pretty high.
Thanks. And are the international partners balking at all about putting their labs on the core complete station without a agreement to move ahead to 7 members?
I believe if you ask the program managers of the international programs, they would say yes. They're very, very concerned. They believe that it would require more than 3 people to take advantage of the investment that they have in the International Space Station and be able to complete what they would like to get done after the deployment of their system.
Thanks. And my last question is, have you scheduled or are you scheduling or doing any tests for a long duration orbiter mission, as the Young report suggested, something on the order of a 30-day shuttle mission?
Are we scheduling tests? The answer is no. If the question was, are we continuing to look at the possibility of flying an EVO flight of some duration as an augmentation to improve our utilization capability once we get the partners deployed, the answer is yes. That continues to be an option that's being looked at as in the trade-off of what we might do in the 04 and 05, 06 time frame. But no decisions have been made at this point. The duration of that, by the way, in the beginning would probably be limited to something like 18 or 20 days based on crew constraints and being able to fly entry after and bring the shuttle back home and land the shuttle, and that would have to be incrementally increased based on our experience base.
This is Craig Cavalt with Aviation Week for Tommy. On the concept of using more Soyuz as crew rescue vehicle to increase crew size in later years, what new perhaps is being discussed with the Russians on that, in overall cost and policy issues within NASA for that?
Well, Craig, as you know, currently, due to what's called a House Bill 1883, we're prohibited from buying procuring new hardware from the Russians along these lines. There are some effort going on to determine what the options are of crew rescue vehicles and the requirements for those versus the options on how to fulfill those requirements. I believe it'll probably be mid to late summer before all of that converges in a way that would allow us to make a statement about what our long-term plans are going to be. There are dialogue going on with all the partners on what we call the in-state options and how to evolve the core complete system to an end state that would be satisfactory to all parties if that's possible. And again, there's a tremendous amount of work and dialogue that must go on between the partners and with the new administrator over the next several months to bring that to a conclusion.
Following on that, are there any creative concepts around the 1883 problem, a la the International's funding additional Soyuz in some manner?
Well, there probably are, but at this point, I'm not prepared to talk about them.
I take that as a yes. One question on S0 truss. I've been in to see that a few times, and its complexity is impressive, if not scary. Tommy mentioned about 475,000 parts for it. Could either of you take a moment here and just kind of wax eloquently on the complexity of S0 and everything that's in it, aside the transporter? Just kind of discuss your thoughts of it.
Mike spent how many years of your life managing
about 3 years,
vehicle systems, so I'll let him answer that one.
A lot of time with S0. S0 is the central distribution system for the power systems. So we have what we call MBSUs that distribute all the power for stations. So all the power from the solar arrays come through S0 and they get distributed to all the systems on board ISS. And so that makes up a large number of the components you see on S0. In addition, all the command and data capability that goes out to the truss to command all the arrays and the cooling systems and all the components out on the truss go through S0, so you see MDMs. We have rate gyro assemblies and GPS systems to let us do attitude determination on the ISS, on the U.S. side of ISS. And those make up the main components that you see in S0. There's quite a few power distribution boxes and remote power control boxes you see out there. And then all the myriad, what you see most when you see S0 is all the cabling that connects all the wires and lines that connect all those components together. But those are the main components on S0.
And Greg, we'll have a full briefing on S0 starting at 11:30 Central Time.
Guys, hi, it's Jim Banky from Space.com. The first question for Mike. On this Canadarm2 deal with the patch that you're sending up and the need to test it, is that a launch commit criteria for April 4th? Do you need to successfully pass that test before you can allow the shuttle to take off?
Well, today that is our plan. We have actually an exception open while we get through this problem. But the software actually is all developed. We've begun preliminary testing, and so we have high degree of confidence in our patch now. We will do all the standard certification testing we do, and then we'll bring it over here to test it in an integrated fashion and launch it. Based on the preliminary testing of the patch to date, we believe that'll all go successfully, and we actually intend to get the patch up hopefully by the 29th or 30th if all goes well. And even though we may not move the arm at that point, we can power up the arm and ensure that the patch came up and that the system is in good shape. And then, as we mentioned, we'll operate the arm on the 1st of April. And today we hold that as a constraint to launch.
And my second question for Tommy, and Tommy, I'm just fishing for quotes here, but could you sort of summarize or remind us with all of the dialogue options, considerations that are out there long term for what you might do with the station and core complete and when you get 7 people up and international partners and all that, what are your current marching orders? How far can you go down with the assembly before you have to stop, or how far out do you know exactly what you're doing and what is it are you going to do?
Well, currently it's our plan is, our core complete plan is to deploy, as we said earlier today, the trusses, the power elements. Then we would follow that with a full deployment of the international partner elements. And the current sequence of that would be the Japanese elements come first in the sequence, then the ESA elements. We also have a SPITM that comes, an extension to the remote manipulator that comes from Canada, and the AMS, a big payload to deploy out on a truss that will need to fit into the sequence somewhere. So we basically have a plan for all of that. At the current time, that plan remains at 3 people for operating the station. And we're currently in the process, as I said earlier, developing an end state that explores the possibilities of increasing the number of crew persons to 6 or 7, depending on predominantly the source of the crew return vehicle. And as I said earlier, I believe that discussion will mature in the late summer or early fall time frame, hopefully in August or September. But there's multiple opportunities, possibilities in terms of how that might turn out.
This is Steve Seislauf again from Florida Today. First for Mike, just a quick clarification, if you will. Is this the same wrist joint problem that you had last summer when the SSRMS was first attached?
We had a couple of problems with the arm prior to or subsequent to 6A. This is similar to one of those problems that cleared itself fairly quickly after it occurred. We were not able to isolate it to a specific joint at that time. The potential exists that it is related to this problem that we're dealing with today. But at that time, we weren't able to isolate it and it cleared itself very quickly. As you might recall, that was on the redundant string. This problem is on our primary string. And so we don't believe it's the same problem, although it is possible that it's similar.
Okay, thank you. And Tommy, is the regardless of the CRV issue, is the station when it's at core complete, can that host 7 people? Does that have the life support and everything you would need, enough room for the sleeping bags, if you will, to host 7 people?
No, not as currently defined. To be able to take care of 7 people, we would need to increase the ECLS capability. We need some increased habitability, increased sleep stations. We also would need to increase the exercise equipment. The current exercise equipment would not provide enough time for a total of 7 people, and would not probably wouldn't last long enough if 7 people was using it 24 hours a day. So we need to increase the habitability and increase the ECL, the life support system capability, as we increase the crew persons.
And that was the last question from Kennedy Space Center. We'll come back to Johnson Space Center for a couple of quick follows, if we could. Marcia?
Marcia Dunn, Associated Press, for Mike. What do you think's wrong with this joint? I guess is my first question. And would you be sending up a spare that's just been sitting around, or was this actually built from scratch in the last several weeks or months?
Well, we have to base our analysis, and since we don't have the hardware at home, we can't tell you specifically. We believe that there's 2 potential problems that we could be dealing with. One is a potential short of some sort inside the wrist joint itself. The other is perhaps noise on the line, which fools the software into thinking that it's got a problem. Both of those are isolated to the wrist joint. We have a spare in the program, always had in the program. It was built when the rest of the arm was built. It was there for this purpose that we intend to use it for now, and that is to replace it if we have a problem.
Have spares for all the joints.
Yes, that's correct.
And I'm sorry, could you repeat when you expect to decide whether to replace this joint in May? And is it you would slip the launch because it takes the crew extra time to train to replace the joint? Is that the issue? And if you decide you don't have the time to do it, would you just bump it to the next station flight? Is that possible to do the main mission without this replaced joint, or could you sort of talk about all that, please?
I can talk about that, certainly. The arm, as we have it today, with this patch that will fly up, will certainly perform the duties necessary for both UF2 and 9A. So we could operate in this configuration. What causes us to be difficult to make our May 6 launch date is not only the EVA training necessary, for the crew, but also the work associated with getting the joint into the payload bay and the orbiter and putting what we call flight support equipment that then attaches to the cross bay carrier and the payload bay. But that's all new work that we have to do. And so those two are the big drivers to why it makes it difficult to make the May 6th launch date. And then we get to what we call beta cutout. And so after we slip about 5 or 6 days, I think, we end up in the beta cutout region that takes us over to the May 31st time frame. So that's what drives us to May 31st if we choose to do this on UF2. And the answer to your question is we could continue another couple of missions. The question is how long do you want to have to do this? And so, as Tommy said, we choose to fix this at this time because the arm is significant to all of the future flights relative to putting the trusses together. We'll decide that in the next couple of days. In fact, we'll have a meeting with the shuttle program today.
And of course, we need to coordinate with our Russian colleagues along the way too. Many of those are down back on Earth today, and will be back tomorrow and so on. So by the weekend, I think this will be behind us.
Mark Carrell from Houston Chronicle. I have a couple. One, can the arm go to the mobile transporter with this problem, or does it need a correction?
It can go to it, yes.
Thank you. And I hope I don't walk off a short pier here with this question, but part of the S0 truss includes the GPS equipment that gives you attitude control cues, as I understand it. That's a Russian function to this point and currently. How soon would you anticipate taking over that responsibility, or would you just sit back and provide a redundant role for some time? What's your plan on that?
We'll let the next team that comes on can tell you the specifics, Mark, but it becomes a redundant capability. The Russians provide attitude determination for us today. What we will do is we will develop our own attitude determination on our side, and then we'll be redundant to each other at that point. As far as when we actually will start using the attitude determination coming from S0, we'll have to spend some time letting the systems work for a while, get comfortable. We have done state vector propagations with the software that's on board today without those systems there, and that's working very well. Bob Castle, hopefully the next meeting, can tell you more specific when we actually start using that data in our attitude control system.
Good morning and welcome as we continue our series of briefings today with an overview of shuttle mission STS-110. With us to give us a description of activities on the flight is Bob Castle, to my right, the lead International Space Station Flight Director. To Bob's right, Jeff Hanley, the lead Space Shuttle Flight Director for STS-110. And to Jeff's right, John Urey, the International Space Station Increment Scientist. We'll hear from each of these parties and then we'll take questions.
Okay. Well, good morning. It's very nice to be here this morning. STS-110 is a very exciting mission, something that quite a few of us have been working on quite a while. It's also referred to as ISS Mission 8A. It's the beginning of Phase 3 of the ISS assembly, installing the centerpiece of the truss on the International Space Station. It's the beginning of, as we say, of evolving, what we call evolving the ISS in new directions. So I think we've got a quick couple of slides here to show the config at crew arrival. This is what the station looks like today. And you can see the U.S. Lab Destiny in the front of this picture and all the other elements. This mission will be adding the S0 truss. Can we go ahead and show the picture of that? So there's the truss. It doesn't look like a whole lot right there, but it's actually the centerpiece. The truss will extend on out. We've got some pictures later on that show the rest of it. But it's this kind of the center point structure for the truss that goes all out, holds the power channels, so the solar arrays. It has all the switching units and some of the power systems, as well as a lot of the plumbing for the cooling systems, since everything kind of comes together at that point for distribution to the rest of the space station. This will be the first deployment of an external truss element, and then of course you'll see missions 9A, 11A, 13A, and on out, adding considerable other parts to the truss. We also will be delivering the mobile transporter unit, and you'll see a little more on that later. It's a base for a future robotics assembly. It allows us to take the Canada Arm 2, which right now is limited to one location. It has to stay on the lab right now. Once we add the mobile berthing system to the mobile transporter on the next upcoming flight, UF2, it will allow the robotic arm to travel the length of the truss. so we can actually grapple things and then roll along the length of the truss to install things at the end of it, which is how we'll be installing the power channels on some of the downstream flights. It also gives us functionality, some key functionalities for U.S. motion control. Specifically, there are a pair of 3-axis laser ring gyros, which allows us to do attitude control, and GPS antennas, which allows us to do both state vector acquisition, determination, as well as attitude, what we call attitude determination. This will be augmenting and essentially making us redundant to the current Russian capabilities for those same things. This will also be the first time we'll do a series of EVAs out of the Joint Airlock Quest. We've done one EVA during 7A, and of course we did another EVA during the stage a month or so ago. Both of those went very well. We'll be doing a total of 4 EVAs out of the airlock. 2 of them will be back-to-back, where we'll do one EVA and immediately the next day we'll do another EVA with another team of crewmen. We'll have a total of 4 EVAs over 6 docked days, and it'll be preparing, essentially making sure it's getting S0 installed, getting it hooked up with power, so all of the systems will be up and running, and configuring it for the next stages in the assembly sequence. And to talk a little more about, let's hand over to Jeff to talk a little more about the details of the mission and the crew.
Okay, thanks, Bob. Before I get into the details of the mission, I'd like to run through real quick some of the folks we have on the team, starting with the flight crew that you'll be able to talk to later today, I believe. If we have a photograph of the flight crew to put up. While we're searching for that, the commander for the flight is Mike Bloomfield here on the lower right of the picture. Mike flew last on STS-97 as the pilot. This will be his first flight as commander. And he has a team of 6 folks working with him to execute this mission. Sitting to Mike's right on the flight deck will be Steve Frick. He will be the pilot, PLT as we refer to him. He's on the lower left in the photograph. And Steve will be making his first space flight and be doing some shuttle robotic arm work, as well as get some piloting time during the fly around at the end of the mission, fly around to the space station. Along the back row in the photograph, you see our EVA teams. We have two EVA teams. The EVA folks are beginning on the far left with Steve Smith. Steve's making his 4th flight to space, and he'll be performing 2 of the 4 spacewalks. He's done 5 previous spacewalks on previous missions, including a couple of missions to the Hubble telescope, and he will be the 2nd most experienced astronaut in spacewalking at the end of this mission, behind another gentleman in this picture, and that's Jerry Ross. Jerry's on the right-hand side in the middle, on the back row. Jerry's making his record 7th flight this flight. He's also completed 7 previous spacewalks and holds the all-time record for number of spacewalk hours for anyone in the program. We have 2 first-time flyers that will be spacewalking for us. Rex Walheim will be teamed up with Steve Smith. Rex is next to Steve on the left here in the back. Rex has previously been working space station systems here with the ground team, and then was assigned for his first flight to STS-110, and we're excited to have him on the team as well. And finally, completing the EVA team is Lee Morin. Lee's also making his first flight. Lee worked again for space station systems primarily in the laptop computer networks, which is a key component of our onboard capabilities on space station. He's now fully trained and ready to go for doing spacewalking, and he's going to get some great experience on our flight here. To complete the team is in the middle is Ellen Ochoa. She's going to be our station robotic arm operator. She'll be performing with the assistance of Dan Bursch, who's on board right now, the actual installation of S0 on the top of the lab. And between her and Dan and Carl, we'll be supporting all the EVA tasks, flying the crew around on the end of the arm and performing the other assembly tasks we have on the flight. On the ground, we're going to have a team of flight directors that will be kind of stand on the shoulders of a bunch of people here on the ground of flight controllers and engineers that support both programs. If we could bring up the flight director photograph, I'll go over that real quick. On the shuttle side, Leroy Kane, lower left. Leroy is our ascent-entry flight director, and he'll come speak with you a day or so before launch about the particulars of the launch. My counterpart on the Orbit 2 execute shift will be Paul Dye. Paul's upper left here, and he's led many missions in the past, particularly in the Phase 1 program. He and Bob both conducted many S1 missions as leads. And making his first flight as a Space Shuttle flight director will be Steve Stitch, who will be our planning shift flight director. And I think we have a very solid team on the shuttle side. On the station side, the same is true. We've got Bob leading the station team. Bob had previously led the shuttle team on Flight 5A, which is, again, one of our most demanding missions to date. And he's on the station side this time and bringing his experience to that. Andy Allgate was his counterpart on station on Flight 5A, and Andy's going to be his other execute shift flight director in the station control room, and making his first flight as a space station flight director for an assembly mission. It will be Norm Knight in the center there. Norm has been supporting the expedition operations since I think late last summer, but this will be his first flight as an assembly flight director. So that's pretty much what I had for the team. Atlantis is our vehicle. She'll be making her 25th flight in total. The last mission that Atlantis flew was STS-110, which is actually what some would consider the close of the Phase 2 part of the ISS assembly, and she's going to open Phase 3 here with the beginning of the buildup of the truss. She's gone through a few months of upgrades and modifications. We have some new solid-state memories, mass memories on board the vehicle. These basically replace some magnetic tape recorders. If you can believe that we were still flying magnetic tape recorders, it's true. But we're starting an upgrade process to step up the solid-state systems. We have a new digital TV system, which we hope to showcase. It's again a new system and has a corresponding set of equipment on the ground here, and we'll be ringing that out during the 110 mission to make sure that's all operational. And we have a new version of orbiter flight software that will be flying on Atlantis. We have a payload bay overview graphic, I believe, that we can show you. Here's the S0 in the cargo bay. You can see that it takes up nearly the entire volume of the cargo bay of Atlantis. The mobile transporter is actually slung underneath the truss in this view, and we also have the orbiter docking system in the shuttle arm, which will be used primarily as a camera platform for the unberthing and installation of S0. Our mission is 11 days. Right now, we believe particularly if we launch on time, we're going to have some margin and consumables to actually have a +1 day at a minimum in our pocket in case of contingencies, which we always like to have. We'll be launching April 4th. We have a launch period of, I believe, 2 to 6 p.m. Eastern time, and as soon as the post-insertion activities are complete, we'll be putting the crew right to bed because we're actually launching rather late in their crew day. Flight day 2 is fairly typical that you've seen on previous missions, where the crew will get out of bed, they'll start checking out suits, they'll start checking out the shuttle arm, and preparing a lot of the equipment for the next day after we dock so that it can be transferred in an orderly way over to the station. And then flight day 3 will be our rendezvous and docking day. Again, fairly standard now. We've got the procedures and techniques for for doing the V-bar approach and docking that you've seen on these last few missions down pretty well. And once the hatches get open, we're going to, Ellen will start working with the station team to start to configure the robotic workstations inside Destiny to perform some of the robotics checkouts. And Bob's going to talk further about the robotics activities and the subsequent assembly tasks. And so I'll just hand it back to Bob.
Okay. We'll pick up with Flight Day 4 after we've docked with the space station. Ellen and Dan pick up by unberthing S0 and installing it on the top of the lab, and we've got a little video graphic of that. If we could run that, this Canadarm2 will reach into the payload bay, pick up S0, and then through a sequence of maneuvers, which have been modified recently, but they'll look basically like this. Move it out over the port side of the combined stack, and then move the orientation around, come up over top of the lab, and then very precisely bring S0 down into the what's called the modular truss segment attached system, or MTSAS. You also hear lab cradle assembly being used. Line that up very precisely, then activate a capture latch, which will there you see the capture latch. The capture latch is actually on the lab. That's S0 coming down. Capture latch looks like a claw. You may hear it referred to as a claw. We'll capture S0, pull the structure together, and then some alignment guides will align it up very precisely. That will all be done in the very first part of the crew day, and then we're timing it so that just as we've finished with the capture latch operations, we'll be depressing the airlock to take the crew, the first EVA crew outside. That will be Steve Smith and Drex Waldheim will be making the first EVA. Their primary job right now really is to do two things, is to one, hook up power cables to S0 so we can feed power to all of its avionics. There's both primary and secondary power and some data cables that go into that, as well as hooking up the first of total four structural attach points, or what we call as strut groups. They will get two of them done on this flight, on this EVA, and the basic sequence of things is they will hook up the two forward strut groups first, then they will deploy the avionics to the umbilical trays, which are actually launched on S0. You'll see the crew actually take them off of S0, install them on the lab, hook up cables at each end, which feeds power to and from S0, to and from the lab. There's another umbilical tray that's deployed on the aft part of S0 that comes down. If you can picture it, it rotates down from S0. There's another one already there from Z1. So these two trays rotate out toward each other and then connect to a large number of connectors in between them on the aft ring of the lab. Then we'll finish up by deploying what's called the trailing umbilical system. The mobile transporter, as you can guess by its name, is mobile. So there's a trailing umbilical that's essentially a flat ribbon cable on a large spool, is reeled out, hooks up to the mobile transporter, and that feeds power and data to and from the mobile transporter. So at the end of EVA 1, we've got 2 out of the 4 strut groups attached, so we're structurally in good shape for quite a while. We're not finished yet, but we're structurally safe. We'll have all the power hooked up, so all the avionics are up and working, and we'll activate S0 and all the equipment on it that evening after the crew finishes the EVA. The next day, Flight Day 5, I tend to think of it as a rest day, but it really isn't all that much rest. It's a fairly busy day, but it's not nearly as busy as an EVA day. So there's a cooling off period a bit for the crew to rest a little bit. They just had 2 very busy days. Flight Day 3 is a very long and busy day. Flight Day 4 is a very long and busy EVA. We'll also set up to do oxygen transfers from the shuttle to the station, transfer some logistics from the shuttle middeck. You won't hear a lot of logistics transfer numbers on this mission simply because we don't have either an MPLM or a space hab, so there's a limited amount of logistics that can be transferred. We'll then pick back up on Flight Day 6. Our second EVA team will go outside, which is Jerry Ross and Lee Morin. They will go outside to do EVA number 2. Their primary job is to install the second set of tripods. These are of structural strut groups. We have bipods and tripods. You'll hear that. The forward groups consist of 2 struts each and a bipod arrangement. The aft 2 consist of 3 strut groups each, 3 struts each, and a tripod arrangement. Each of these deploy out, attach to the lab. There's an expanding collar that allows their length to change. So they attach them to the lab and then tighten down the collar so that the length can't change anymore. So you wind up with a fairly rigid structural member when you're done. They'll also remove the keel pins on S0. Those are there for the S0 to stay in the payload bay. And if you can picture it, I think we've got a picture later on, but essentially you have the S0 truss, you have two keel assemblies, and the mobile transporter is right in the middle. That was all there for structural loads during launch. Clearly you got to get rid of these two keel assemblies so the mobile transporter can move back and forth along the truss segment. We'll finish up with the other trailing umbilical system cable. There's a redundant set of those cables, so we want to get redundancy hooked up to the mobile transporter. We'll finish EVA 2, bring the crew back inside. They will do their post-EVA work and then immediately do the pre-EVA work for the next day. And the next day will be flight day 7, EVA 3. And again, we'll have the first team that goes back out. So essentially the EVA teams just alternate. They'll go back out. Their primary job this time is to essentially change the power feeds to the Canada Arm 2. It's currently powered through power feeds in the lab. We want to switch it so it's being fed from power feeds on the truss. So when it goes to the mobile transporter, it can be fed from power up on the truss. So that's the primary job we're doing there. The complexity there is we really don't want to power down all of Canada Arm 1 all at once, on Canada Arm 2 at once. So we're going to bring it down one redundant string at a time. So we'll power down one string, do the power reconfigurations, power that string up, verify it works, then we'll power down the other string of avionics, change the power reconfigurations there. There are a couple other things that go on during flight day 7. This one's a major use of the shuttle arm. We actually put a crew on the end of the shuttle, Canada Arm 1, I guess. It's just so they can access the work sites easier. We do a few other things, releasing the mobile transporter launch locks, restraints, get the mobile transporter ready to move. We are going to move it during mission 8A. If everything goes well, we'll have the SSRMS back up and running, and we use Canada Arm 2 to install an airlock spur, which is just a translation aid, makes it quicker for the crew to get from the airlock up to the truss area. Again, for downstream flights, they're going to be doing a lot of work in the truss area, so this just makes it a lot quicker and easier for them to get from the airlock to the truss and back. Flight day 8, as we continue to go through the mission, this is another day that for the crew is probably their quietest day. We've tried hard to keep that a quiet day. We will be doing the mobile transporter checkout. We'll actually translate it from its launch position to one of the work sites, and then we'll translate it to the other work site. We will leave it in position that UF2 wants it, because UF2 brings up the mobile berthing system, which attaches to the mobile transporter. We want to put it in the right spot for them. On flight day 9, we'll pick up with EVA 4, the final EVA. I'm not going to go through all the list of things on the EVAs. Again, Dina Barclay, our lead EVA officer, will have a briefing later today. Flight day 4 is where we pick up. EVA 4 picks up all the rest of the EVA tasks. The main thing to note is EVA 4 is a bunch of get-ahead stuff. If nothing on EVA 4 gets done, we have had a very successful 8A mission. All of the critical things that have to get done in the first 3 EVAs. And that, again, is by design. If anything doesn't get done in the first 3 EVAs, we'll do it on EVA 4. And if something falls off of EVA 4, it's things that can be picked up downstream, either by stage EVA or by the downstream flights fairly easily. And again, that's by design. We chose to keep our margin rather than have a day that we could do an EVA if we wanted to. Said, let's just go ahead and do the EVA, and we'll do a lot of stuff it's get-aheads for downstream flights. It's good to do, but we can take it for other activities if we needed to. And then that's the rest of it is shuttle undocked, and Jeff will talk about that, and then we'll pick up with John.
Flight day 10 is going to be our final goodbyes day. We'll be doing some final transfers in the morning, final transfer of equipment back to the shuttle that'll be brought home with the shuttle crew. We'll have our final handshakes, close the hatches, and perform the undock and fly around late in the afternoon for flight day 10. Flight day 11 is a standard day before entry, cabin stow, STS checkout, checkout of the flight control system of the shuttle, getting ready for entry. And then flight day 12, which falls on April 15th, will be our landing at the Cape. And that's the mission in a nutshell, and we'd like to hand it to John now for some payload discussion.
Thank you, Jeff. Good morning. It's good to be back here again, this time to talk about science coming home, going up on 8A, as well as what we'll do during the 8A stage on board ISS. Expedition 4, as I've mentioned in previous briefings, is the busiest, most diverse, and most complex research program of any ISS expedition to date. So far it's been highly successful, and we look forward to continuing that success after the 8A flight. So we're going to talk a little bit about the science going up and down, as well as what we'll be doing during the stage. If I could have the first slide, I'd like to just spend a little time talking about where we've been so far. The chart shows the number of payloads we've done on the first 4 expeditions. So cumulatively, we've operated or continue to operate about 33 payloads, many of which are still in progress or operating today. These have supported 47 separate investigations from the U.S. as well as from 9 other international countries. We've put in nearly 700 hours dedicated to research on board ISS and racked up about 70,000 hours of experiment runtime. Through the UF-1 flight, we've launched nearly 4,700 kilograms of research hardware to ISS and returned about 1,000 kilograms of hardware samples and other data products. Next, I've got a short video clip. It was filmed by the Expedition 4 crew back in January, but it's still fairly current. Shows a general layout of our research racks as they'll be during the 8A stage. And this opening shot, we're looking forward toward the hatch where the shuttles normally dock. Overhead, you can see Express Rack 2 with the microgravity barrier in front of that. We're panning over to Express Rack 4, which is our continuously powered rack. Currently, it has the BTR biotech refrigerator operating. It has our samples from the CBOS experiment. They'll be coming home on 8A, of course. We also have 2 STSs in the lower right there, as well as the plant experiment, the ADVASC, which is also coming home, and they'll be replaced by other powered payloads. Okay, we're back at Express Rack 2 now, and you can see that the barrier, which is really to prevent objects or crew members from bumping into the rack. That's the rack we use for really microgravity sensitive payloads. Okay, we're back over to the HRF rack, the Human Research Facility, which supports our human investigations, such as PUF, the pulmonary function experiment, the interactions, and also all of our data downlinking for EVARM and some of the other experiments, and also has a workstation and ultrasound located within the rack. We're going to swing back over to Express Rack 2 and kind of do about a 180, I guess, or 270, because they are in different orientations. What you'll see there is the controller for the Eris ice experiment, which is the one that's characterizing the active rack isolation that's in Express Rack 2, which we will use for the first time in its intended purpose to support an experiment during the 8A stage. I'll talk a little bit more about that experiment later. You also saw a glimpse there of Express Rack 1, which has one of our microgravity measurement systems, the MAMS, and a couple of the SAMS sensor head drawers as well. And those will be continuing, of course, through 8A and through the rest of the ISS program. Now we're looking forward toward Node 1, and we're going to dip down into the deck where the lab window is located. Through the window, which is, you see there, of course, the shutter is closed, so you can't see through it. That's where the crew Earth observation and the EarthCam activities typically take place. You saw in that rack location, the crew has touched a lot of the cameras, the 70 millimeter, 35 millimeter, and the electronic still cameras that they use for those activities. And they typically like to keep the window covered just so to make sure that nothing scratches the window pane. We did a window survey recently and did notice there is a scratch pane on the inside that is replaceable, and it does already have a few scratches, but that so far is not interfering with any of the science activities we're doing. And finally, we do have Express Rack 5. You'll see that in a moment. Currently, we're using that only for stowage, and the crew also uses it to stow a lot of the camera hardware and things like that, so it's close and adjacent to the window location. Of course, on future expeditions, we will use that rack for some powered experiments, probably starting sometime next year. So in a nutshell, that's the bulk of our research capability on board and our major facilities. During the stage 8A, we will have 15 payloads that will be operating and using a lot of those facilities to characterize the microgravity environment, study human physiology. Also, for the first time, performing research in fundamental biology. I'll talk some more about that in a minute. Continue some materials processing. We also have an external payload out there, the MISSI, that's looking at external exposure factors. Continue some biotechnology and commercial endeavors, as well as earth sciences. Since 8A is not an MPLM or SpaceSat flight, we're somewhat limited in what we can bring up. We have about 270 kilograms of research hardware coming up. and we're bringing back about 130 kilograms of hardware and samples on this flight. Okay, to talk in more detail about some of the experiments, I've got a short video clip that talks about an exciting new experiment. It's the first one from the Ames Research Center in the area of fundamental biology, called the Biomass Processing System, or BPS. If we could have that video clip. Basically, it's a two-locker, mid-deck locker unit that'll sit in Express Rack 4. It has 4 growth chambers that will be used for 2 different purposes. One is just to test and validate the hardware. It'll be shaken out in various modes to make sure it can control the environment for the plants. The hardware was built by a company called Orbitech up in Wisconsin. Dr. Robert Morrow is the principal investigator for the hardware. Dr. Gary Studi at Dynamac Corp at KSC is the lead for the science team. Each of the 4 chambers will be growing different plants. 3 of the 4 will be growing super dwarf wheat, both used for the test validation of the hardware as well as for the science experiments. And the 4th chamber will grow a plant called brassica, which is something we have grown on Mir as well. Both of these plants are fairly well characterized on the ground, so we know how they should respond. That's one of the reasons we picked those well-known plants. So 2 of the chambers will be used for science. As you can see, the chambers are removable, and the crew indeed will remove them during the mission for several things. Obviously, you have to care and feed the plants, so the water and CO2 regeneration systems will have to be refurbished. And also, there'll be some serial harvest during the flight, just to determine how well the plants are growing in microgravity. So it's very exciting for that team out at Ames, and they're very much looking forward to having that experiment kick off. Okay, if we could have the first of the series of slides. Human life sciences, we'll be continuing some of those activities during the stage. The interactions, the weekly questionnaire, this crew has already been doing that since December when they went up. They'll be continuing on a weekly basis. Pulmonary function, the PUF experiment has been very successful to date, both in just the monthly checks. In fact, we've got one of those going on today, as well as the pre and post EVA studies the crew has done, and we'll have one more session during the 8A stage as one of the regular monthly checkups. The next slide is the renal stone experiment. The first 2 sessions have been completed. This is a training shot with the 2 of the Expedition 5 crew members. And we have one more session to do during the 8A stage. Then the EVARM experiment, looking at the radiation inside the suit. This was done for the first time during the February 20th EVA, and we'll be doing that during the 4 EVAs on the 8A mission. We have 2 additional pre and post flight experiments. Of course, the pre-flight testing is done. On the left is a bone experiment looking at changes in bone demineralization. And also the one on the right is a cardiovascular investigation, if you will, looking at peripheral circulation, how it changes before and after long duration spaceflight. Switching over to microgravity, we'll continue our microgravity measurements, both with the MAMS and the SAMS units in the various frequency ranges. To date, since these units went up on the 6A mission, April of last year, they've returned more than 500 gigabytes of data down to the ground. In the fluids physics experiment, the colloids experiment's also been up there since the 6A mission last year. Unfortunately, the hardware suffered a failure back in late February. We've been troubleshooting that. So far, we've been unsuccessful in getting the hardware to work. We may have one or 2 more things to try. We'll be looking at when to do that, probably during the 8A stage. So we hope we can get this recovered and continue with science. If anything can be said, luckily the failure occurred fairly late in the experiment program, so most of the science has already been completed and the data has already been returned to the ground. In biotechnology, we just have one experiment. It's a simple PCG dewar, protein crystal growth dewar. This is the 4th time this hardware is making a trip to ISS. Of course, we flew about 7 of these back on the Mir space station. This is capable of flying hundreds, if not thousands, of protein samples for crystallization, and also this particular project involves high school students who are able to load their own samples into this hardware. In the commercial arena, we have 2 new experiments going up. One is the CGBA commercial generic bioprocessing apparatus. This is actually a reflight of the experiment that failed during the Expedition 2. The commercial customer, Bristol Myers, is interested in pursuing this activity, looking at bacterial fermentation and how potentially antibiotic production may be enhanced in microgravity. So we're looking forward to hopefully having a successful flight with this one. And lower right is the CPCG, or commercial protein crystal growth. Second time this unit is flying to space on ISS. The first time was highly successful back on Expedition 2. We do have one new commercial endeavor, the zeolite crystal growth. Zeolites are compounds. I like to think of them as rigid sponges. They can absorb liquids or gases without changing their shape or their size. They're used very much in the petrochemical industry for in terms of gasoline production and so forth. So anything we can do in these microgravity experiments to enhance the quality or quantity of the crystals produced would certainly have lots of benefits here on the ground. The furnace unit, which you can see in the upper right in Express Rack 2, was launched back on UF1. We did a checkout a few weeks ago, and it looked fine, and we'll be putting our first samples in there during the 8A dock phase. Crew Earth observation, just some cool pictures. The Expedition 4 crew has sent down, and they've been actually very good. We've got over 1,000 electronic pictures already returned, plus whatever film products they'll bring back with them. Just a short series here. This is the coast of California with San Diego roughly in the middle. This is the Chesapeake Bay on the East Coast during the wintertime. And this is right here in the Clear Lake area. You can see the Clear Lake City and Clear Lake and Galveston Bay in the lower right. And of course, they'll be continuing that during their stay on board. And finally, Missy, which is our first external payload, launched back on 7A1. And we got some pictures back during the EV on February 20th when the crew was out there, and we noticed that there are some of the samples are changing, either discoloring, or some of the foil samples are actually peeling back. So we definitely know that there are some impacts from being out there. These samples will be up there for about another year when they come back on the ULF-1 mission early in 2003. As I said, there is some science returning on 8A from things that have already done during the Expedition 4. At the bottom, you see the CBOS, or cell science experiment. This was actually conducted back in December, and since then, the samples have been in the biotech refrigerator just awaiting their ride home. In the upper left, there's actually 2 of these protein crystallization facilities, the STS units. We have been activating and deactivating the crystallization cylinders just to see what the time course effects are. Most of those are being deactivated now, and they'll be coming home on 8A. And in the upper right, the ADVAST, or Advanced Astroculture. This is a plant growth experiment from University of Wisconsin. Unfortunately, what you see there are the plants that were actually grown during Expedition 2. During this flight, the plants are not growing quite as well, and I guess that kind of shows that you really need to make sure the parameters for plant growth in zero-G are fine-tuned, and that's why we do a lot of these experiments. So in a nutshell, Expedition 4 has been highly successful to date, and we look forward to completing the science program with 8A and during the 8A stage. As always, you can always find details about the ISS research program. Marshall Spaceflight Center has a website, scipoc.msfc.nasa.gov. With that, I'll turn it back to you, James.
Okay, thank you very much. And with that, we'll take questions starting here in Houston. If we have any questions. Anybody? Okay, over here, Mark. And please state your name and affiliation.
Mark Perot from Houston Chronicle. Probably for Jeff, I wonder if you can bring us up to speed on the cooling system problem they had on the last mission, and whether that has turned out to have any impact on Atlantis.
Sure. When they got Columbia back at the Cape, you may have heard they found a piece of debris in the cooling system at an orifice in the plumbing, and this was the leftover debris from the brazing of the fluid lines when they were serviced and upgraded. That's an isolated, I think, considered an isolated incident. And Atlantis has not shown to have any kind of concerns in that regard. So I don't see that that's going to be a factor for
Okay, thank you very much. And I wonder if you could sort of address this question sort of philosophically. The security overall for the mission, the launch, the landing times will be obscured and for a later time, and other measures are being taken. Can you sort of give us, from a philosophical sense, what it is that you're attempting to sort of accomplish with this approach, and to the extent that you can, just how you deliberated this as an agency to sort of come up with a strategy?
Well, I can honestly say that I wasn't a party to those deliberations, so I'm not the best person to talk to about the philosophy that went behind it. I have, we've all been given the policy, and we've stated a launch period 2 to 6 p.m. Eastern Time on April 4th. Beyond that, I believe that probably the best people to answer your question are the folks at headquarters that put out the directive.
Further questions here in Houston? Okay, up here with Marcia.
Marcia Dunn, Associated Press. Probably for Bob, but maybe Jeff too. Did you finally figure out the problem with the Quest with the odor after the last spacewalk with the cartridges? I mean, is that going to affect you at all as you go into these sets of spacewalks? And if there's any problem with Quest, can you go out the shuttle airlock if you need to?
Okay, let me try and do those in order. Yes, we believe we understand what happened with the odor. That was regenerating what we call the metal oxide canisters, or MEDOX for short, which are used to remove carbon dioxide from the station, or from the suited crew members during the EVA. The 2 canisters that got regenerated had been left in the regeneration unit for a long period of time. They'd been there for over 6 months. And we believe what happened is they'd absorbed other chemicals from the air, just trace contaminants, trace elements that are always there. But a lot more of it had been absorbed than we had expected and was anticipated. So when we regenerated them, all those chemicals came off the air. It turned into a sweet-smelling kind of odor. We duplicated that type of behavior on the ground with some canisters that were also kind of left open and exposed to just the open environment for long periods of time. When we did that, we also went back and said, let's take a really thorough look and make sure, since clearly there were some things, trace elements in the atmosphere that were not accounted for when we designed the system originally. People are taking a very careful look. They've been doing some additional testing out at one of the test facilities, and we believe we're going to be able to use the metal oxide during the 8A mission. If we can't use it, we are flying, as a preventative measure, we're flying on the space shuttle several regular LIO canisters that have been normally used, have been used for over 100 EVAs on the space shuttle. And we have enough of those canisters to do all of the EVAs on the 8A, plus our contingencies that we're going to carry in the shuttle middeck. So if we use the metal oxide on orbit, then those canisters will come back. They'll be redistributed and reused. If we, for whatever reason, we don't get comfortable with using the metal oxide, then we'll simply use the LIO. And I think that's a very smart move by the program. This way there's no pressure. If we get comfortable with metal oxide, we'll use it. If we're not comfortable, we'll use the LIO, and no big impact. And the final answer to your question, yes, we could go out the shuttle airlock. We have consumables on the shuttle. We guaranteed we'd have at least enough consumables for 2 EVAs out of the shuttle, and realistically, we're going to have consumables to do them all if we needed to. The major impact, if we had to use the shuttle airlock, is obviously I've got a vacuum between the 2 vehicles now, so I can't distribute the crew between the vehicles the way I'd like to. For example, we want Ellen on the station flying the Canada RM2. If I do a EVA out of the shuttle airlock, she can't be there. She has to be on the shuttle. So it'll impact our operations quite a bit. It'll slow things down because we won't be able to put Ellen and some of the other crew members where we want them. But yes, we could accomplish all the major objectives and all our critical tasks we could do out of the shuttle if we needed to.
And what are the most spacewalks you could do on this mission? Counting, you know, if you run into problems, how many times can you go out the door with the crew, and how much extra time would it take to install the truss if you have to go to the redundant string without the proper joint?
Okay, well, let's see. We'll probably be limited as much by time as we are by consumables. We can do at least 5 EVAs. We know it's set up to do that. And we'll probably have consumables to do more. I haven't really thought through it, but we'll probably run out of crew time before we run out of consumables. If we have to go to the redundant string, or Actually, it's confusing. The redundant string, we call them primary and redundant. The primary one has the failure, so we're going to use the redundant string as our prime string. I wish we'd named these differently, but we didn't. It really depends on when the failure occurs. If we have a failure on the redundant string before we've gotten the S0 installed, then we'll have to go send the EVA crew out to drive the wrist roll joint, and that got talked about a little bit by Mike Saffredini. Depending on when the failure occurs, it might take as much as 3 extra hours to get things installed, so that comes out of EVA1. So EVA1 will not do all the things that it set out to do. We will hook up what are called the launched activation cables. There's some special cabling hooked up that was deployed on the 7A1 mission that will allow us to power the S0 avionics without really installing it, without installing the struts, without getting the avionics umbilical trays off. Essentially a set of jumper cables that we can hook up. We'll hook those up. We'll make sure we got the power on to S0. That may be all we get done, depending on when the failure happens. But we can get S0 installed, get everything, all the avionics powered up and safe on EVA1. Mike talked a little bit about the SSRMS. The robotics community here has done a fantastic job. It's kind of a three-pronged effort with CSA building the software patch to allow the prime string to operate on 6 joints. The robotics team here at the Johnson Space Center has come up with joint positions where the wrist roll only has to move once, and still make the trajectory make it look so much like it used to that it's a very minor crew training impact. And then all the loads verification people have looked through all of this, because now we'd have one brake turned on. Normally you'd always have all 7 off for a lot of things. And the total loads community, both in Canada and here and in California, have done a great job validating all of that. So I feel very comfortable that if we needed to use the Canada ARM2 on its prime string with only 6 joints, we could certainly get S0 installed. It would slow us down for some of the EVA support tasks, but I feel very comfortable we'd figure all those out and get there quite handily with the ARM. So the worst it would do is slow us down by about 3 hours on the first EVA.
And you could do all the succeeding 3 EVAs, there would be nothing left out, or
probably some of the content from EVA4 would be left out.
Oh, because of the time.
Because of the time.
Okay.
But again, the EVA4 is designed, we can leave content out.
Right.
But everything from the first 3 EVAs would get done.
Okay, and one last question. You worked pretty intimately with the lab mission. This has been called the most complicated piece of hardware just under the lab. Could you talk about that, how you look at this and see the S0 truss as being, why is it so complicated? Why is it so intricate? And how close does it come to the lab in terms of those 2 areas?
Okay. Well, on this mission, I don't think it's as complex. This mission is not as complex in terms of activating new hardware as the lab mission was, as 5A was. S0 has got a lot of components on it, a lot of equipment on it, but to be honest, probably half of it is not really doing anything right now. It's there so that when we add other components on each side of the S0 and the power channels outboard of S0, then those components will be very busy and will be very active. But right now, they're not doing a whole lot. We've got cooling systems that go up on the P1 and S1 truss elements that go up on 9A and 11A. Well, they're not there right now. So yes, they have to interconnect and cross-connect. There's a lot of plumbing to do that, but it's not doing anything right now. There's a lot of power switching components that are essential when you have the power channels hooked up on the end of the truss. They're not there. So it is a very complicated piece of hardware, but a lot of the complexity is turned off right now because it's not needed until we add the rest of the elements. So from that perspective, I thought the lab was much more complex because virtually everything in the lab came up and started working when we got the lab installed. So that complexity-wise, I think it was. The mission 5A, I think, was more complex activation than the mission 8A is. Now, the number of EVAs and the number of structural things we're doing is much more complex on 8A than it was on 5A. So they're complementary.
Okay, and I believe we have questions from the Kennedy Space Center, so we'll go there now for those.
This is Phil Chen-Arthurs. Pardon me if I mixed up Bob and Jeff because I'm used to seeing you guys as flight directors in the opposite rooms. But I guess for Jeff, what kind of ascent margins do you have on the shuttle? How different will things be with the Block 2 engines? And I suppose I'll just get down to prop margins. What do you have, and how many fly-arounds does Steve Frick get, assuming everything works out for Sigma normals?
We've got about 2,200 pounds of ascent performance at this point. I think Leroy's going to come talk to you very shortly before launch, and he can give you a lot of the particulars on Block 2 engines and what that means to us. The fly around, I think we'll do the full one and a quarter or 1.5 laps around right now is what we're planning to do, and we have the propellant margin to do that. We in fact had enough propellant margin to add a small objective at the end of the mission for an Air Force payload that we're flying. So and that particular payload requires an ohms burn. So we had propellant to do all that, plus cover some station reboost. And that's by virtue primarily of the fact that while we have S0 in the payload bay before we dock, we have to hold back a lot of propellant in the ohm system in case we had to bring S0 home. But once we dock and we basically hand S0 to the station, all of that propellant now is available. And so we end up with quite a bit of propellant to be able to use for things like that later in the mission.
And I guess for Bob, can you update us on the beta joint issue with the P6? Did the thermal covers on UF1 do any assistance as far as smoothing out the roundness of the gimbals? And after you add the S0 and a bunch of extra mass, how much more difficult will it be to keep on moving back and forth from LVLH to XPOP attitudes? Are you going to still have to do that until the P6 is moved out to the end of the truss?
Okay, let's see. Let me try them in reverse order. Yes, the baseline had always been we'll be switching back and forth between LVLH and XPOP all the way out until P6 moves. I think it's out to 12A.1 actually is where we stop switching to XPOP. So we'll continue to be doing that. As far as the beta gimbal assembly on P6, the folks, engineering guys tell me that yes, the thermal blankets did do what they were expected to do. It did smooth out some of the thermal variations that they were seeing, but we're still seeing problems with the beta gimbal. We're still seeing current spikes in it, and we're starting to see similar things on the other beta gimbal to a much lesser degree, but we're starting to see similar type things. So I think that is a concern. It is something we're trying to minimize the rotations that we put on those beta gimbals. But right now we feel that we have a plan that's going to keep them working essentially until P6 moves, and then these joints don't have to move very much. They just rotate back and forth to track very slowly as the sun beta angle changes. So they're still acting up a bit, but we think we've got them under control to where they'll last as long as they need to, and then we'll move P6.
This is Jerry Hanna from Time magazine, and I guess this one is for Dr. Uri, and I go back and do my homework. But what are you feeding the beautiful, I guess, 2 months growth of wheat? Do you add any nutritional supplements like manure or whatever to the formula? But that was good, healthy looking wheat.
Yeah, to be honest with you, I don't know the exact formulation of the nutrients. I can get back to you on that if you'd like. But yeah, the first on the ADVAST, certainly the first crop we did back on Expedition 2, they did very well. On the ADVAST on this flight, they're not doing quite as well. We think there might have been some overwatering early on, and that delayed their growth. We're still considering the experiment successful. You always learn from that mistake, but. And as far as the wheat we're going to see, what you saw in the video for the BPS, that was of course a ground-based experiment. We hope to see that kind of growth when we get on orbit.
Okay, thank you.
This is Steve Seislaw from Florida today. Forgive me if I missed this earlier, but how much time and transition room do you save by leaving from Quest instead of the shuttle?
Okay. Don't really save a lot of time. The real purpose from leaving from Quest instead of the shuttle is so I can keep hatches open between the vehicles, so I can hopefully use the MEDOX, which is a regenerable system. But it's mainly to allow us to more efficiently do the missions by keeping the hatches open. It don't really save any time. I can prepare for an EVA about the same amount of time in either airlock.
Okay, thanks. And for Jeff, y'all have done this construction work, and it's all gone as smoothly as it has been, most say remarkable. But does this cause any complacency on y'all's consoles? In other words, are you kind of hurt by the prior success you've had?
Complacency doesn't even enter into it, because each one of these missions poses their own challenges. Certainly, the success of the 3A through 7A time frame is something that we want to build on. The Mr. Holloway likes to refer to assembly as kind of a mountain climbing. And in that regard, you could think of 7A as being base camp. And now we're going to start the real ascent of the summit, and it's going to be a long climb. I really thought that was a very appropriate metaphor to use when in his correspondence to the rest of the team. The summit's getting clearer with every flight. With this flight, we'll start to build the truss out. That's a key enabler to the rest of the program. It's going to provide the power to add the partner elements and do the other things that we want to do. So, no, I think 8A is challenging in its own right, and we are as much attuned to detail in terms of our attention as we were for 3A, 4A, 5A to get that series of flights flown.
Jim Banky, Space.com. I guess a question for Bob. You got Z1, P6, S0, S1, P1. I think I got it in order so far. As I recall, when Z1 went up, I think it was described as the backbone of the station by some of us, and I'm wondering if that was the case, then what is S0? Is it another backbone, another piece? Is it laying the cornerstone to something? How would you describe it in those kind of construction terms?
Well, in a construction term, I guess it's kind of the centerpiece of the truss. It's the center of the truss. It's what the rest of the truss elements build out on. And I think that's what I would call it. And as Jeff said, the truss elements are very important because that gets all the power modules up, which is what allows us to add all the partner elements. We're rapidly approaching the point where we're going to be power limited. We need to go ahead and build the truss out and get the other power elements online.
This is Phil Chen of Earth News again. I guess for Jeff, can you address the issues with transferring the oxygen and nitrogen on UF1, and I assume it's been taken care of, and what happened, and what did you do to correct those issues?
Yeah, there were a couple of issues on the UF1 mission. As you'll recall, there was an oxygen hose that goes from the output of the pump that pumps shuttle oxygen into the station tanks, goes from the output of that device to the station tank plumbing. The crew was concerned that because the outer sheath was deformed on that hose, that perhaps the hose itself might be damaged. So to be conservative, we did not go ahead and use that. We also had a problem with the ventilation hose that cools this pump device. And it turns out that it was the wrong hose, essentially, and so we're taking up a replacement hose, air duct, if you will, and a replacement, or not a replacement, but the original high pressure hose that was flown on UF1. We brought it back down, we've sent it out to White Sands and tested it, measured it, cleaned it, done everything that we needed to do to convince ourselves that the hose is in fact good and safe to use. And we'll go back up there, and on flight day 5, we'll have the crew set up the device we call the Orca, which is an oxygen recharge system that will be used to pump oxygen from the shuttle to the station. We'll set all that up on flight day 5, check it out, and hopefully let it run for some amount of time to replenish some of the oxygen that we use during the first EVA. Some of the issues involved in that are safety concerns with respect to, we want to make sure that we keep that system very clean. High pressure oxygen systems can be a little bit temperamental, but we've gone through great pains in not only the materials that have been chosen, but the training involved of the crew to make sure that that system stays clean and that we don't have any safety concerns. So we're fairly confident that if we can get these Orca components installed and Orca activated, we can transfer quite a bit. Our plan right now is to transfer about 120 pounds or so of oxygen from the shuttle to the station on this flight.
This is Steve Seislaw from Florida Today. I have a quick question for John, and that is, you're reflying this Bristol experiment. I'm just wondering if other commercial companies are lining up now to do research on the station, or is that something that's still kind of in limbo?
Yes, Steve. No, actually, we do have commercial customers lining up. We wish we had more opportunities to fly them. There are some new companies that just are asking for a flight early next year. We're looking to try to get them manifested probably middle or end of next year. That's the earliest slot we have open for them. So they are lining up. Bristol Myers is one of them. Amgen had a successful flight back on UF1, looking at the anti-osteoporosis drug, and they have asked for a reflight because it was so successful. So yeah, we do have numerous ones that are out there, and we hope to get them all flown as quickly as possible.
Okay, and I believe that's the last question from the Kennedy Space Center. We can come back here, I guess, for 2 follow-ups. These gentlemen have a commitment we have to get to in just a couple of minutes, so we're going to have to make it kind of quick here. Mark?
Mark Carreau from Houston Chronicle, and probably for Bob Castle, although I might be confused about who's doing station and shuttle this time too. But how does this brake issue manifest itself as a problem? I'm not sure exactly that I understand what it does with the brake not release in the roll position. Is that sort of the issue here?
Yeah, that is exactly the issue. The brake did not release on the roll joint, wrist roll joint. And the system is designed, we commanded all 7 brakes to release, one of them did not, and said, okay, there's something wrong, let's safe the system, and essentially took power off the brakes again and reapplied all the brakes. So the patch is to allow it to operate with the wrist roll brake left on, and just the other 6 joints will move.
Okay, thank you very much. That really did clear that up for me. And for Dr. Urey, I think I counted 5 racks currently aboard. When you get to core complete, how many racks will you have on the station for science?
Well, that's currently somewhat under review, depending on how many we can actually fly. But we will have 10 in the U.S. lab within the next year. We got 2 going up on UF2 and 3 more on ULF1 next January. And then, of course, when the partners modules come up, we'll be adding additional racks there too. But I can't tell you the exact final number right now.
Marcia? This will be the last close up.
Marcia Dunn, Associated Press for Bob. You mentioned you're going to test out the mobile transporter. Who operates that? Does the crew have any involvement whatsoever, or is it all ground control?
Most of the checkout will be done under ground control. The actual moving of the mobile transporter will have the crew do, so they'll be watching it and paying attention to it just to be ready to safe it if anything goes wrong. I don't anticipate a problem, but the crew will do the actual motion of the transporter.
And how fast?
It moves at 1 inch per second, and as to how far it goes, I don't remember the distance between work sites 4 and 5, but it's obviously slightly shorter than the truss is long, so something in the order of 30 feet, I would guess.
Good afternoon. I want to welcome everybody here to the STS-110 briefing on the S0 cargo element. What I'd like to try to cover today is a little background on the S0 element, some general features and characteristics of the S0 element, talk a little bit about the history of how we got here, how we built up the element, and how we're now on our way to the pad, and then a little bit of an overview on the S0 and the mobile transporter subsystems. In reality, the S0 cargo element is really 2 pieces, and that's the way the briefing will be conducted, mainly the S0 truss element and the mobile transporter. And let's go ahead and start with our first animation, which I believe is the payload bay. As you can see, we pretty much fill up the payload bay of Atlantis on this flight. The S0 truss element is 44.2 feet long. It weighs 26,716 pounds. And the span of the 44.2 feet is from starboard to port when it's installed on board the station, or forward to aft, as you see it here in the payload bay picture. There's been some discussion and ways of trying to capture some of the characteristics of S0 and its complexity. And what I'd like to try to do is present some information and features on the S0 element in a couple of different ways so that you can kind of judge the intent and the complexity of the element. The first thing I'd like to do is do it visually for you. Here you see a very interesting shot of the S0 truss element that was taken last year when we were on our way to a very important set of integrated test operations called the Multi-Element Integration Test Program, MEIT, and I'll go into some more detail about that a little later. The reason why I like this picture is because it shows almost all of our avionics and equipment installed on the S0 truss. And the thermal blankets, which you'll see when we get on orbit, are removed, so you get an opportunity to look inside the bays, see the myriad amount of cabling, connections. We have a lot of fluid connections in there, some of our solid piping in there for the ammonia system, cold plates, etc. So from a visual standpoint, I think it conveys to you that S0 is more than just a truss element that some people may generally think of as just a girder or a piece of structure, but it has a lot of functionality with it as well. Now, the second way I'd like to try to convey to you a little bit about the complexity of S0 is just to talk about some of its characteristics and features. Some of the major components and systems that we have on S0 deal with power distribution for the space station in what we call our main bus switching units, or MBSUs. We do power conditioning on S0 with our DC to DC converter units. We have secondary power control and distribution through various remote control switching devices. We have 4 suites of computers on board S0, 2 of which actually control all the other truss elements external to the space station, and 2 which control the components within S0 itself. We have the critical components for the United States orbital segment GNC elements, that being the GPS antennas, and our laser rate gyro assemblies. We also are the central gathering point and distribution for all external video on board space station. We carry 3 video switches up that collect video from all the externally truss-mounted cameras, all the cameras on the SSRMS once it steps over onto the mobile base servicing structure. And it also does all the conversion of the video from copper to fiber and back again to fiber as required as it goes between the interfaces, both externally and internally, ending up with the video inside the laboratory on our workstations. It also is the central brains for our structural monitoring system. We have multiple strain gauges, accelerometers, and other types of instrumentation, not only on S0, but on all the other outboard truss elements. All that information is gathered into our signal conditioning units and provided for downlink. We have additional instrumentation on board S0 that will monitor the external environment around the space station. We're actually flying a charged particle directional spectrometer that will allow us to be able to monitor the radiation environment around the space station. So these are all some of the key features and functions. Now, again, to try to capture what all that means, all of the power distribution for space station, once we're in the assembly complete phase, when we have our outboard arrays, will come through S0's switching units and be able to be distributed to the other modules, the other truss elements. It will also provide us, for the first time, a cross-strap capability. So if we were to lose a power channel in one area, we could then augment that from another array channel through the switching unit. So that's a fairly important feature. Again, as I mentioned earlier, all the command and control aspects of the external truss are captured within S0. We have 2 computer systems that communicate and provide the bridging and the architecture between all the other truss elements and the laboratory's central computers. We also have, as I mentioned, all the external video processing. We have our GNC functionality, which will be for the first time giving us the opportunity to do our state vector and attitude determination on the U.S. side, allowing us to do our antenna pointing, array pointing, positional information in orbit, etc., as an augmentation to the current capability we have with the Russian segment. And then lastly, we have the mobile transporter, which I'll treat a little later in more detail. But that's going to provide us a mobility with our robotic servicing systems and capabilities that we don't currently have. Right now, the SSRMS is locked in on the lab PDGF and can't really have the range of motion it needs to do the assembly of the space station. So those are 2 ways of trying to convey that. A third way is just to kind of talk about the sheer numbers of it. I think it's been quoted a little earlier today. There's about 475,000 parts that are inventoried on this element. To give you a bit of a comparison, the laboratory, U.S. Laboratory Destiny was slightly over 50,000. Also, keeping in mind that this is the key structural attachment point for the buildup of the external truss element. So that kind of gives you an idea of where S0 sort of fits into the program. Okay, let's see. I believe I'd like to go, another way of conveying some of this is going to our next image, our next view, which sort of shows you what S0 reaches out and touches. That's another way of trying to getting a little bit of an idea of what S0 is like. These are all the elements in the life of S0 that we will actually touch, interface with, and provide services and capabilities for. And let me just real briefly sort of go around in a clockwise fashion. If you start at the top there at the noon position, you see the Z1 element. The primary interfaces we have in that area are power distribution. We accept power from Z1 early on before we have the outboard truss elements and the outboard arrays. And then after that outboard array system is completed and P6 is relocated, we return the favor to Z1 and provide its power for the rest of its life. The next element going clockwise in about the 1 o'clock position, you see the P1 element, and exactly opposite of that is the S1 element, so I'll talk about both of those together. We provide the main structural attachment point for both of the central thermal system truss elements, as well as a pass-through for the ammonia services that go not only within S0 itself, but also to the other truss elements, and we'll talk about that a little bit later in a little more detail. We also, as I mentioned, do the acquisition and distribution of all the external video off of these elements, and we do acquisition, conditioning, and distribution of the structural monitoring information. The next thing a little bit further down to that is Node 2. The parts that we play in Node 2 are rather significant in that our utility trays provide all of the power, data, and cooling services down to Node 2 when it's launched on 10A, and through Node 2 to the international partners. So we use Node 2 as a remote distribution service for those services. The next key item is Destiny, the laboratory, and here our main purpose is structural attachment. S0 is the keystone or the central point of the external truss elements, attaching all the truss elements to the module pattern. So we'll show in some detail on how we do this, but that's where our main structural contact is made between the truss elements and the modules. We also have pass-through service capabilities for ammonia cooling. We eventually provide power to the lab once again we are distributing the outboard array power systems, and we also are the protocol and architecture interface to all the command and control aspects. The next thing in the picture is the mobile transporter, and we'll get into some more details on that a little later, but that is our mobile servicing area. It interfaces with the mobile servicing base structure and the SSRMS and gives us the range of motion we need to complete assembly. There are 2 of the 10 work sites that are throughout the entire 350-foot truss structure space station on S0. Those are work sites 4 and 5. From the airlock perspective, we provide a structural interface there also. We have the airlock spur, which makes a connection to the airlock and provides a translation path when the crew members are exiting for EVA. And lastly, on the Unity node, we provide some power distribution through S0, again from the outboard assets. So that hopefully captures a little bit of the flavor and the characteristic of S0. Now, what I'd like to do is talk a little bit about the history of the S0 element and how we got to where we are now poised for launch. The mobile transporter and the service module started on separate but soon to cross paths in their development. In April of 1997, the first structure of the mobile transporter was forged and built and sent out to the West Coast for assembly and build-up. The mobile transporter continued assembly operations through about 1990. At the same time, the truss elements began their build-up. We can have the next image, please. The top left image is a rather nostalgic one for a lot of us. That is the first bulkhead built for S0, and that activity began in July of 1998. The structure you see in the bottom right corner is the scaffolding and build-up assembly that we had at the Huntington Beach facility. As we forged and built the different truss components, we laid them in this lattice structure and built up the S0 element. Then about June of 1999 and July of 1999 respectively, the S0 and MT elements were shipped to the Kennedy Space Center for assembly and operations build-up. That continued on until we began our next major interface testing, which was MEIT2, our multi-element integration testing, which started in September 30th of 2000. I'd like to point out in this picture right here, you can see the S0 truss elements right in the middle of the picture. It's flanked on either side by the 2 truss elements that have the white box-looking structures on the top. That's S1 and P1 respectively. Now, if I could get the next image, I'd like to show you this. This one right here actually is quite remarkable in my mind. This shows a rather high view up in the space station processing facility. And what you see here is a rather historic moment. If you start at the very bottom of the picture in the right corner and work up, you see the P4 truss element, the P3 truss element, the P1 truss element. In the very center, surrounded by most of the dark scaffolding and the equipment that goes out to the middle of the aisle, is the S0 with the lab emulator and the node emulator. Then just beyond that, you see another white set of boxes. That's the S1, and the truss just beyond that is the S3. So at one time, back in September, we had all except for S4, all of the external truss elements laid out in this facility, wired up, functioning, talking to each other, and operating and simulating the various missions that each of these elements we brought up on, and also the power conversion and power transfer operations that we have to do when we go from the inboard power system to the outboard power system. I'm not an expert on the history of manned spaceflight, but I believe that this probably ranks up there as one of the high points, because I don't think we've had this much equipment of a human spacecraft lined up and operating at the same time in quite a while. So that was quite a milestone for us. The next picture shows where we are with S0 today. This is the final closeouts of S0. This picture is about a week old. It shows all of our thermal shrouds in place. It shows our attachment structures, which I'll get into a little bit more detail in a minute. And we, at this point, are prepared and ready to go out to the pad. And I got a status report from Kennedy just before I came in here. We're probably about 30 minutes away from lifting S0 and placing it in the canister. So we're progressing on quite rapidly here today with some milestones to go meet the orbiter out of the launch pad. Okay, the next thing I'd like to talk a little bit about is the S0 systems itself, and sort of step through some of those to give you some additional characteristics. What I'd like to start with is the attachment structure. We actually have two types of attachment devices, or classes of attachment devices on S0. We have one that's a temporary device which captures and positions and holds S0 so that we can do the necessary work for the permanent attachment structure, and then we have our permanent system itself. In a moment, I want to take a look at the animation, but before I do that, I want to just mention to you there's two pieces to this positioning structure, which we call our Mobile to Truss Structure Attachment System, or MTSAS. We have the active side, which is currently on orbit. It's on the laboratory, U.S. laboratory Destiny. And as some of you may remember, it was actually used, previously used on the Flight 6A mission when we took up the Canada 2 arm. It was the structure and operable system that we used to hold the Space Lab pallet in place while we assembled and erected the Canada 2 arm, and as it stepped off of that platform onto the laboratory. So that's the active piece of it. The passive piece is on the S0 side, and that contains some alignment devices and a capture bar, which allows, and I think you saw this earlier in Mr. Castle's presentation, the claw, as we call it, to grab a hold of that bar and pull S0 down in place. The reason why that's important is we have to put a preload on that interface in order to rigidize that interface and be able to do our other EVA activities. So if we could take a look at the animation now. The top part is S0, the bottom part is the laboratory. When Mr. Choa brings us into position, we'll come down, and there are some fine alignment guides, some V guides that allow us to settle in. Then the claw will close in and pull us down and preload that interface. There are some conical devices on that interface that fit into some cups that allow us to preload that interface and give us the kind of rigidity and structure that we need in order to go off and do our EVAs. Now, just to also kind of get you a little bit oriented about where we're going on the vehicle, if we could have the next still, please. Here is a picture that was taken during the UF-1 mission, and just slightly in the shadow of the laboratory there, just back from that shuttle line, that is where the active side of the MTSAS is located. The next image shows you where we're heading with S0. This is a rather interesting shot from the 7A mission up on the P6 element, and where we'll be heading with the S0 element is in between the P6 area and the nose of the orbiter. And you can see the attachment structure there about midway up the laboratory. Okay. Now that we've talked about the temporary attachment structure, I'd like to talk a little bit about the permanent attachment structure, and that is our module to truss structure attachment system and the adjustable struts. We'll start the animation here in just a minute, but what you'll see with that animation is we have two basic groups of attachment struts. We have a bipod, which is a two-strut configuration, and a tripod. And if we could go ahead and start with the animation, please. This being the S0 truss, on the back side here, you'll see our two attachment devices, two types of attachment devices. We have two forward devices, forward bipods, and we have two aft tripods. These are stowed flat against the face of S0. When we get on orbit on EVAs 1 and 2 respectively, The forward bipods will be deployed by simply swinging the V-shaped structure down, and the tripods will kind of extend out, sort of like teepees out above that. Each of those strut groups end in attachment plates, and those attachment plates have EVA bolts that have to be actuated. Those attachment plates and bolts all match up to the laboratory interfaces, and later on in the mission what we will do is we will disengage that temporary system, and these struts will then become the final attachment point for the truss and the module system. The next item that we want to talk about is our airlock spur. This is a translation path and structure for the astronauts. This device is deployed away from the starboard face of S0 into a position where it intercepts the airlock Destiny and attaches to the ring structure on there, providing an easy and direct path out of the airlock hatch to the truss elements, and then using the primary translation paths along S0 to the other truss elements. Next time I'd like to talk about our GNC components, our guidance and navigation control components. The rate gyro assemblies you can't see here because they're underneath the blankets, but here you can see our 4 global positioning satellite antennas, again providing state vector determination and attitude determination. Also on that face you see our 2 avionics trays. These are stowed flat on the face, and during EVA-1 these are physically removed by the astronauts and transported over for installation on the Destiny laboratory. These are deployed on the port and starboard side of the laboratory and provide our primary power interfaces from the laboratory to S0, and eventually we reverse that service and provide power back to them. As long as we're talking about the power system, we'll keep looking at those components. Our next major components are the MDSUs that I spoke about earlier. Here's our main distribution and switching units. Our next elements are our power conversion units. These take primary power and convert them to secondary power. You see 3 of them along face 1 inside the truss here. Our 4th one is on our wedge surface. We also have on that surface some components for EVA. These are components which will eventually be built up to make the portable work platform, and basically give the crew a capability to operate off the SSRMS, similar to what we've done on the SRMS, giving them a sort of a cherry picker ride and being able to work off of the SSRMS. Also on that face, you'll see some umbilicals that are segment-to-segment fluid umbilicals. These are the primary connections between S1 and P1 and allow the ammonia flow between the 3 elements. Also for 9A, we have our segment-to-segment attachment structure. This is a simple capture claw and arrangement to pull in the 2 truss elements and snug them up against S0. The aft lab tray contains many of our services between the lab and the S0. This is also deployed on EVA-1. And the little stanchion you see off to the side there carries services down to the node as well. The last item that we want to show in this view is the removal of the keel pin and drag links. As you can see, it's on the same surface as the mobile transporter, and so these have to be, the keels have to be removed and placed on this wedge face in order to free up the rails for the mobile transporter operations. Now I'd like to talk a little bit about the mobile transporter system. And starting out by saying that as the mobile transporter translates up and down the space station, it has to be provided services for power, data, and telemetry. The way we do that is we allow the mobile transporter to basically have an extension cord that it can carry along with it, called the trailing umbilical system. It's a flat ribbon cable that provides those services. Let's see if we can get to the next photo here. You can see this is where the mobile transporter is located on the bottom of S0 for launch. And if we can go to the next graphic. This shows a general layout of the mobile transporter itself. And what I'd like to do is step through some of the key systems that we see on the mobile transporter. The mobile transporter itself, by the way, just for statistics, is about 102 inches by 107 inches, weighs 1,923 pounds, and has a top-end speed unloaded of 1 inch per second. When we're crossing across various truss joints where we have to be very careful as we transition across that, we have to drop down to a speed of about 0.06 inches per second. So nothing happening very rapidly there. The next graphic, we'll talk about our linear drive unit. This device is basically like the motor, the transmission, and the brakes of your car. This is what makes the mobile transporter go. It has two drive devices on it that engage the rails and through friction allow the mobile transporter to go up and down the rails. The next graphic illustrates our load transfer units, and as its name implies, it takes the loading off of that drive system that I just mentioned and places it into a more structurally sound interface on both the rails and the mobile transporter. This is basically 4 claws on the corner of the mobile transporter that engage specific locations on the rails and specific interfaces on the rails so that you can have a nice rigid platform to do your robotics operations off of. When you're moving the SSRMS with a large mass on the end of it, such as another truss element, we need to have this rigid interface, and that's why the LTUs are there. The next graphic shows a caricature of the roller suspension unit. This is basically what keeps the mobile transporter on the rail. There are 5 spring-loaded wheels that apply force and tension in both the X and Y direction on that I-beam, and that keeps the mobile transporter secured and gives the drive unit friction so they can drive along the rail. The next picture, this is an actual photo of the roller suspension unit. The 2 blue circular devices you see there toward the center of the picture are 2 of the 5 wheels that we just talked about. Our next graphic shows the location of our buffer amplifiers. These are electronic devices that are stored inside the mobile transporter and basically take the signal that comes up and down the TUS and make sure that we have the proper balancing of the signals as well as boosting the signal, since we do have to deal with 175 foot in one direction and another 175 foot in the other direction, spanning the full 350 feet across space station. Next picture, please. Here, we'll be taking a look at the TUS. This is that extension cord I was telling you about. There's actually 2 of these real devices on either side flanking the rail face of S0. The TUS system itself actually provides a tensioning and a rate operation as the cable goes in and out of the rail structure. And it also has, about every 4 or 5 feet along the rail, sort of a gatekeeper device, which is our cable retention system and keeps the cable flush up against the rails. Here's a picture of the TUS cable coming out of a TUS reel. The cable itself is rather interesting. As I mentioned, it's a flat ribbon cable. It contains both the power, data, and video services through this. The outer surface there, as you see, is a white surface. There's also just underneath that white surface kind of a blue insulation surface, and we use that to monitor wear and tear on the cable, similar to what you do with your tires when you look at your tread wear mark on your tires. If we start seeing blue come through that white, then we know that that cable is wearing down, and it's time to change it out before we have any sorts of problems with the electronics inside. Now, before we go on to the next part, I'd just like to explain one other thing. As I mentioned before, there are 10 work sites throughout the length of the truss structure of the space station. These work sites also have 2 umbilical devices or plug-ins that allow the mobile transporter to wheel up to this location and plug in. We need that in order to operate the SSRMS. The TUS does not provide us the services for the SSRMS. So the power, data, and control aspects of the SSRMS are controlled through these umbilical devices. And if we take a look at the next animation, here you'll see highlighted the active side of those umbilical systems. These are the ones that physically engage into the locations at each of the work sites. Now on 8A, we will actually be exercising the mobile transporter. During EVA 3, we'll go out and remove several launch restraints and configure the drive system so that it can operate. Our plan is to go from the launch position down to the starboard side of S0 and to our work site 4 location. Then, in order to check out of the drive mechanism in both directions, we'll drive all the way back to the other end to work site number 5. And then to prepare it for the reception of the MBS on UF2, we will return one more time across the span of S0 and lock it down at work site 4. I believe that's the extent of my comments and description on S0. I hope I've been able to capture a little bit of the features and some of the characteristics of it. I would like to take just a moment, though, if I could, to give a couple of quick closing remarks. We are here poised, ready to launch S0 because there were an awful lot of people across this country who spent a lot of time and a lot of effort to get ready for this. That includes our contractor organizations, our design centers, and all the other NASA centers. And what we tried to do is to make sure that in representing the folks here that we were able to capture the spirit of the team and the importance of the truss element. So we tried to do that with our cargo patch, and if we could have that last animation. Here, the key features are that we have the 3 stars symbolizing the beginning of the Phase 3 construction, and the other significant feature of this is the general shape of the patch, which is that of a builder's keystone. S0 is the keystone for the start of the Phase 3. It's also the keystone for the external truss. And with that, I think I'll turn it over to you.
Okay. Thanks, Ben. We'll start with questions here at the Johnson Space Center. Please remember to state your name and affiliation. We'll start with Mark.
I'm Mark Carruth from the Houston Chronicle. I had a couple of, I think, pretty quick questions. During the ground testing, do you know about how many hours you did these interface tests? I mean, how thoroughly did you wring out all this? Was it just power? Did you do data and fluid and everything? Can you kind of go into that a little bit?
Oh, yes, I'll be happy to. No, in fact, that's, to be honest with you, the amount of effort that went into this is a real tribute to the folks down at the Kennedy Space Center, both the Boeing troops and the NASA troops. Just to give you an idea, the MEIT testing alone spanned from September 30th, 2000 to June 25th of 2001. During that time period, we fully activated all the truss elements. We fully activated the ammonia systems without the radiators. We did not deploy the radiators, but we had an offline simulator that allowed us to flow ammonia offline and come back on. So we did all the ammonia charging and operations. We translated the mobile transporter, probably not in MEIT, but probably about 6 to 8 times up and down the S0 truss element. In fact, that was quite an interesting feat as well, because we had to build a special set of ground support equipment that basically neutralized the weight of the mobile transporter and lifted it up on an air-bearing ski that allowed it to go up and down underneath the S0. So the ground equipment was almost as exciting as the flight equipment, to be honest with you. We did all of the power operations as far as activation. All of the command and data systems were activated. We did a full transition from P6 power to outboard array power. We did a full power module activation. We did a full comm system check. As you know, when we go up with S1P1, we bring up additional S-band assets. We did a full check out of that. So basically what we tried to do, maybe I should have said this in summary, is we tried to look at the missions as a whole. We tried to find out what are the critical steps in those missions, and then build a test around it to make sure that each of those critical steps were exercised, just like we would do it on orbit, just like we would do in the order from the 12A mission, 12A.1, 13A mission, etc. So it was a rather extensive operation. And that was just for the integrated part. S0 has probably undergone thousands of hours of testing by itself as an element, because when we first arrived at the Cape, we did not have all of our avionics fully integrated. So we did a lot of integration at the Cape and a lot of buildup at the Cape. We even went through, sort of as a final point, on January 18th to the 23rd, we went through what was called our post-software load S0 initialization test. Now that's a long title for basically we took the final version of the flight software, loaded it in S0, and went through all of the critical initial activations that we'll have to do on EVA-1 to make sure that S0 is safe and functional on orbit. Now, we didn't do the full S0 activation, but it was what was necessary to make sure we'd be safe on orbit. So I hope that gives you a little bit of a flavor of the extent of what we went through.
Thanks. And well, I may have misunderstood this, but is the mobile transporter U.S. or Canadian?
U.S.
Oh, it is?
Yes, sir. It was built by Astrotech. It was a subcontractor.
Okay. More questions? Marcia?
You mentioned 44.2 feet long. What? How wide?
Oh, I should have given it to you. And in fact, I have
all the dimensions that you've got.
Okay. That the width from trunnion to trunnion is just a little bit under 14.5 feet thereabouts. The reason I mentioned that is it's considered a full volume payload, so it spans the entire width of the payload bay. In fact, we sort of encroach a little bit into the standard 90-inch envelope because we've got so many items hanging off of S0. So we pretty much fill up the payload bay and take that full expanse.
So the 14.5 feet is sort of a diameter?
Trunnion to trunnion.
Okay. And what's the main material that the truss is built out of?
It's the typical stuff we've used with various types of steel and aluminum alloys for our truss elements.
And I'm wondering if you have a cost and whatever cost you give will include the mobile transporter. Or is that
yes.
separate?
The breakout that I have is that for the S0 truss element, the estimate is $600 million. The mobile transporter is $190 million. For about $790 million total for the integrated element.
Thank you. And I'm wondering, when you do the railroad car test, what speed do you anticipate? I mean, will this be super slow because it's a tryout, or will it go this fast 1 inch per second? And it seems like you'll just traverse the entire track. And what happens if it gets stuck? And what do you do?
Let's see. Let me take your first question. We'll actually be varying the speeds as we go along because we want to check out the different modes of the mobile transporter. So we'll be doing both loaded and unloaded. So you'll see a varying velocities. And I don't recall, I'm sorry, I don't recall him. My memory says we don't probably get up to the 1 inch max. I don't think we do that on this flight. And by the way, that's just a design spec. We don't normally operate at that velocity. Let's see now, the next question you had was, sorry.
We'll traverse the entire track?
Yes, we will traverse both sides. The reason why we're doing that is we want to get a check out of the drive system in both directions. I didn't have a graphic for you, but there are two sets of wheels in that drive assembly. So as you change directions, you can also change wheels and change operations. So we want to do a full check out of both systems so we know that we've got both directions and both systems working properly. And then your question was, what happens if it gets stuck? We do have two locations on the S0 truss that are called work sites 4 and 5. Those are important to get to from a load standpoint because that's where, as I showed you, the load transfer units can grab onto the rails and hold rigidly. And it's also where the umbilicals are hooked up for the mobile system operations. If the mobile transporter, however, were to get, on this particular flight, were to happen to get stuck in between, there's really no urgency or no terrible concern about staying there for a little while because all of the services necessary to support the mobile transporter come through the TUS. So since we don't have anything bolted on the top of there and nobody dependent on us, we don't have to get to one of those work sites. Now, we don't want to leave it there because, again, the drive system is designed to provide a certain amount of tension and load on the rail for translation. It's not designed to handle heavy loads. That's why we want to get to the worksite locations for the LTUs. So in this particular instance, again, docking and undocking loads would not be a problem for us. So it staying there for a little while would not be an issue. But we couldn't execute the installation of the MBS and the step off of the SSRMS onto the MBS on UF2 if we didn't get it at a work site. So what we have is a capability, and I don't know if you noticed that on the general graphic of mobile transporter, but you'll see these little knobs that seem to be sticking out of every one of the boxes. Those are all EVA overrides. So if we had a problem with one of our drive units, we could go out there and disengage that drive unit manually, and we could re-engage the alternate unit if we needed to, or if that whole system were not working. We have a backup plan where we could actually push it down the rail until we get it to a location, and then engage the mechanisms at that point. So we have backup capabilities to be able to do that.
I mean, or could you wait till May or June?
We would probably want to do whatever we could on this mission to make sure that we got the mobile transporter back to one of the work sites. Because that's the whole point in the checkout, is we want to ring out the system and make sure that we understand all of the nuances of our new transporter device here. But we could wait to a later operation or a later time and just say during a stage EVA if we had to try to do something. But our whole intent, our whole purpose of doing this kind of exercise was so we had the STS-110 crew there available to us where we could do inspections or perhaps even take off ORUs and bring them back if we've isolated them to a particular ORU so we can work on it.
David Santucci with CNN. What is the first mission where the mobile transporter will be critical?
Well, on the 9A mission, we plan on having the SSRMS on the MBS structure and on the mobile transporter for the reception of the truss element and for the installation. Now, the actual traversing does not happen on that flight. We only traverse on 11A, where we go to the other side and do the port side installation. So from a motion standpoint, it's probably 11A, but because we want to start operating off of the MBS as soon as possible, then we will probably say it would be critical and important to us on 9A.
And as far as the S0 is concerned, I know that it's a sort of a building block for more to come. How does it benefit the station right now, just as the S0?
I think the one thing that comes immediately to mind is our guidance, navigation, and control capability that we're adding. We will be activating the GPS antenna system and the rate gyro systems during the 8A stage period. We've got about a 1 month to 6 week trial period with that system, where we'll be running through and doing satellite acquisitions and doing maneuvers to test the gyro assemblies and so forth, and feeding that information into our guidance, navigation, control computers and our software, and establishing a capability on the USOS side. So I would say that's probably the one that jumps out immediately at us. The other thing is that once the mobile transporter becomes functional, then we have a lot more reach capability, because it's up higher on the truss than where the SSRMS is down underneath the lab. So now we have robotics access to a lot of the P6 ORUs that we currently do not have. So if we needed to do a maintenance operation or an inspection or some type of contingency operation on P6, it's much, much easier to do that off of the MBS than it is underneath on the bottom side of the lab. So those are the things that come immediately to mind.
Okay. That's all of our questions right here at JSC right now. We'll move now to the Kennedy Space Center. Again, please remember your name and affiliation.
Hi, it's Craig Cavalt with Aviation Week. Thanks, by the way, for that really thorough briefing.
Thank you.
Would it be accurate to call the whole integrated enchilada here the most mechanically complex piece of the station?
Well, you're asking a very biased individual here, because I've lived with SEO for a long time now. I would say that it's fair that it's up in the top 2 or 3, if not probably the most complex in my opinion. And the reason why I say that is because it has so many interfaces that it reaches out and touches so many things on space station. It has so many EVA interfaces, and I'm sure that the next presenter will go into much more detail in this, but there are so many interfaces that we have, both planned and unplanned, for maintenance and for backup and contingency. It just has an awful lot of widgets and an awful lot of places to go poking around with tools. So I would say, in my opinion, that that's a fair statement. Yes, sir.
And on the software side of things, does the addition of it, does it bring up quite a bit more lines of code on its own, and is there a way to characterize that?
Yes, sir. And in fact, I'm embarrassed. I actually had that information in my pitch, and I went right by it. Let me just, if I could, for a moment, touch on that. We go through several software upgrades on board the station as each of the elements come up. But we had a major software change on board the station back earlier this year on February 22nd, 23rd, when we actually did what we call the R2 transition. There were several hundred thousands of lines of code that had been sent up pre-stored on the computers that we changed out, and some patches that we actually uplinked. There are on the order of 6 to 8 what we call software modules in the different functions on board station, like the CNC function, the GNC function, etc. Every single software module on that station was touched by this change. The reason why is because we were modifying the control aspects of the space station as a whole to take into account all of the truss elements that are coming up this year, 8A, 9A, and 11A. As I mentioned, there are brand new capabilities that are coming up with S0 that we did not have the code for. There was a large change in the GNC, as you might imagine. There's also going to be a large change in the SSRMS, because I think in an earlier briefing you heard that we're changing the power configuration so that we're no longer receiving power from the lab, but we're receiving it from the truss element itself. Well, that changed a whole lot of code as to where we monitor the power, how we distribute the power, and so forth. So it was a major step up in our software, and like I said, several 100,000 lines of code. The execution of that, I'm very, very proud to say, and I'm speaking for a lot of folks who worked on this, went almost flawlessly. We did the transition, like I said, on February 22nd and 23rd. The space station has been running and purring along perfectly from a software perspective ever since, and it was a major step up in the software. The next major step up that even comes close to this will be in the 12A, 13A time frame when we go to the outboard power system arrangement. And then we have a very large code step up we call R3 at that time. But that was a very astute observation on your part. It did require a lot of code and a lot of change on how we operate space station to bring up S0.
Okay, thanks. And just one kind of in the form of a listing of contractors, if you will. In addition to Boeing, kind of cite who else is a major player?
Oh, that is truly an unfair question because I know I'm going to forget somebody and make somebody mad at me, but I'll do the best I can. Before the consolidation, we had McDonnell Douglas, Huntington Beach. The power components and some of the acronyms may seem similar to you from the 4A mission. A lot of our power components came from the Canoga Park facility, similar to the P6 element. As I mentioned, Huntington Beach was the primary truss builder. Astrotech built, as a subcontractor to Huntington Beach, built the mobile transporter. Many of the fluid systems, cold plates, and things of that nature were built here in some of our facilities in Houston, as well as some of the facilities, some of the other Boeing facilities in Dallas and other locations in Texas. So I think those were probably the main players, and I'm certain as soon as I stop, I'll think of someone else. So my apologies already to those I've forgotten, but that's what comes to mind at the moment.
Ben, this is Jim Banky of Space.com, and you like to believe there's no such thing as a dumb question, but this may actually be one. It has to do with how the truss is attached to the Destiny laboratory and the unique properties of microgravity and weightlessness in outer space. It seems that at home, if you want to put a big TV, for example, up on the wall, you definitely have to find a stud to drill the thing into so that it'll hold. If you just put it on your wall board, it tends to not last very long. Putting this S0 truss on the skin, what looks like just thin skin of the Destiny laboratory, doesn't seem to make sense. Could you describe how that is possible and how, just from a structures and outer space point of view, that all works?
Yes, sir, and you caught me again. I got behind in my narration of our tour of S0, and I forgot to bring this up as well. We are not actually attaching to the outer skin of the laboratory. What we do is we had designed attachment plates on the laboratory that tied directly into the load-bearing rings underneath the skin. So in essence, that's exactly what we did. We found the studs in the wall of the lab, and we tied straight to those load pads. And these are the same primary load-bearing rings that we used for the trunnions and the keel pin when we launched the laboratory. So when you, and I believe there'll be some more detailed discussion of this in the follow-on presentation by the EVA folks, but you'll see there's an attachment plate on the laboratory that comes down. It has a soft dock feature where the foot of the bipod or tripod click in, and there's a series of bolts that you go in a particular pattern and torque that down, similar to putting a tire on a car. You torque it down and lock it down in position. It has a very high preload capability, very large bolts, and it's tied directly to the load-bearing structure. So that was an astute observation on your part, and you caught me skipping a part of my narration I shouldn't have done.
This is Phil on Earth. What's your thermal clock once you remove it from the shuttle's cargo bay? At what point would you have to hook up the emergency power cable that they've got sitting up there just in case versus the normal hookup time of the cables in the first EVA?
Okay, we actually have a couple of thermal clocks I'll need to pass on to you. The first thermal clock is during EVA 1. We have done a preliminary pre-flight analysis that assumed worst-case attitude and worst-case beta conditions. And in that analysis, we required having power and the power cables hooked up in S0 operating in the 16 to 20 hour range. What we're doing this week, as a matter of fact, is we're going back and looking at the actual flight period, the actual beta angles for that flight period, and already we're seeing an increase in that number up into close to the 30-hour range. So worst case, 16 to 20 hours, we're probably going to see something in the 30 to 35-hour range based on the actual launch time and the actual beta conditions. Now, that's our first clock. Our second clock is on the mobile transporter. The mobile transporter has a separate power system from the S0. It comes through the touch rail, so we have to connect that touch rail up. That particular element is a little bit more robust, both on its location and the fact that its equipment is a little bit better shielded. So we have something on the order of 35 to 38 hours on the mobile transporter. Now, what our plans are in the EVA, and I would also ask you to see if this is covered in the follow-on briefing, or certainly follow up in the follow-on briefing. We have gone through and very meticulously looked at all the operations on EVAs 1 and 2, and we have what we call bingo numbers along the way. So that as you progress through the EVA, you have to have accomplished a certain amount of activities in order to proceed along the normal path of going and getting those forward avionics that I showed you. If we fall behind, we can make a call at a number of points, 3 or 4 points during the EVA, that says, okay, when we finish this particular task, we're going to now have to go off and install what we call our LTA cables, our launch to activation cables, that were previously rerouted on board station during the 7A.1 mission, that will give us the minimal services we need on S0 for survival. And it's been very well articulated and very well sculptured in that EVA that we have several go, no-go points to see whether we should proceed or not. So that protects those first 2 thermal clocks. The third and final thermal clock actually comes somewhere in the EVA 2 or perhaps EVA 3 time frame, depending on when we do some of our power reconfigs. And that's when we power down a one-hole channel in S0, do some rewiring and reconfiguration, and then power it back up again. In that instance, we have on the order of 24 hours plus, because, again, we have secondary heaters that are already running on the channel that hasn't been brought down, and so we're not really terribly concerned about that third and final clock. But those are the clocks that we have ticking. And I think the bingo number answer got your question on when we might want to hook up the contingency cables. Was that okay?
And for those of us mechanical engineers who really hated our statics and dynamics courses, when you first mate the S0 using the claw mechanism, at that point, is the shuttle safe to leave, or do you have to get the struts in place? How many of the bipods and tripods do you have to get into place in order to be able to have another shuttle dock or Progress or Soyuz dock? What are the constraints there and the various permutations if for some reason you don't get that stuff in place? Okay, let's walk through that. When the empty SAS claw is engaged, it puts a few hundred to 1,000 or so pounds of preload on that interface. At that point, we've specifically analyzed and looked at this very carefully and tested that interface. You are now safe for undocking of the shuttle. It handles both the minimal amount of vibration you get in the docking system release as well as the pluming effects. So we looked at both of those effects. So once the claw is fully engaged, you are safe for undocking. However, you are not in a configuration from a structural standpoint to sustain docking loads. In order to sustain docking loads, we must have a minimum of 2 struts attached in a particular orientation. Our normal plan is to install the 2 forward struts. If you can imagine the picture, you have the 2 forward struts and the claw in the back, so you make a nice little triangle. And so that's the general footprint or the load footprint that we're trying to create. If for some reason we have any difficulty with the forward struts, we can use the aft tripod struts as well in any combination as long as they are adjacent struts. What I mean by that is you should not have a forward strut, a claw, and an aft counter corner strut, because now what you have is a door hinge, and that's not the configuration we want to be in. We want to be in a stable configuration of a tripod. So that is the condition with the claw and the minimum struts that we need to sustain subsequent docking. Now, the question you didn't ask, but I'll go ahead and throw it in as a bonus, is how many struts do we need in order to complete assembly? In that instance, in order to complete the 9A mission, we need to go ahead and have the minimum of the 4 struts engaged, but we can have some bolt-out conditions on those struts and still meet the assembly requirements.
This is Steve Seislaw from Florida today. I just have a quick question, and That is, will the mobile transporter give the arm any kind of reach over to the Russian side of the house, or is this totally just to service the whole truss section?
Unfortunately, we can't reach we don't get that much additional reach off of the mobile transporter MBS configuration over to the Russian segment than we currently have off of the laboratory. The advantage you do get, however, is you get to come over the top of the truss and get a little bit more access back on the node area, but it doesn't really extend the reach very much back into the Russian segment area.
Okay, I believe that's all our questions at Kennedy Space Center. If we have any additional questions here in Houston, Mark?
Mark Ruff, Houston Chronicle. I had just one, and I probably missed this. I apologize. But when do you plan the test of the mobile transporter to move it? Is it between EVAs or after the? I just got lost on the top.
Oh, sorry, that's quite right. We do the configuration of the mobile transporter, the release of the launch restraints, and the engagement of the drive mechanism on EVA 3. EVA 3, and then the day in between those EVAs is when we actually do the translation and the operations. So it is in between EVAs.
Mark, anything further? Marcia?
Marcia Dennis, Associated Press. I sort of got the impression that this truss segment is far more intricate than the next two that are going on. Is that so? The next two will be simple by comparison, or no?
You're going to put me in trouble because I share offices with the other launch package vendors on those two, so you're going to put me in trouble by saying this. No, I think that as far as most of the equipment is concerned, the diversity of the equipment, yes, we have a little more on S0 than we do on S1 and P1. Where S1 and P1 has its complications, and I'm putting in a plug for the downstream flights, is that is our central thermal system. And managing ammonia on orbit, especially in the large quantities that we're talking about, and the mechanical operations of those radiators and managing those is not a simple task. In fact, I think when their briefings come along, you'll see that there's a very fascinating rotary joint system that is on there to manage those arrays so that we keep them thermally conditioned and we don't get too hot or too cold. And that's a fairly complex piece of gear. So I think maybe our diversity on S0 as far as the type of systems we have might put us a little bit over, but when you look at the function of those other truss elements, you'll see some complexity there as well.
And a quick question about the railroad tracks. How far apart are the two tracks, and what are they made of?
Well, actually, they span the wheelbase of the mobile transporter, and the width of that being about 102 inches, so it's probably about 80 inches apart. For the rail. I'm sorry, what was your second question?
The material that the rails are actually
It's the same material as the truss. We use the same steel compounds and aluminum compounds.
Back behind you, baffled, Mark.
Thanks, Mark Carruth from the Houston Chronicle. I just wondered if there was anything terrestrially in the civil engineering realm that you know of, famous landmarks, buildings, or anything that sort of has something comparable to this piece of equipment?
Well, that is a tough question. I'm not sure, but I can. I think of it more, I would think of it somewhat like this. When you have a large skyscraper structure, you have to have certain basic components in there. The things that anchor a lot of the load-bearing members to the foundation, that allow you to build outward, that allow you to put in the walls, support the floors, and so forth. I think the structural aspect of S0 is very similar to that core foundation piece. It's where the loads are all tied back into, and it's what holds the modules and the truss elements together. From a function and servicing standpoint, it's almost like it's the central servicing center down in the basement, say, of the building, where your power and your communication and your video are all routed and processed through. So any large skyscraper or complex building like that has that kind of demanding load interface and then has that diverse servicing requirement would probably be something that would come to mind.